live on YouTube.
Hello.
हेलो हेलो इसका कम है हेलो हेलो इसका कम है
आप ये यूज कर लो सर।
इसका थोड़ा वॉल्यूम
हेलो हेलो।
इससे इसका कम है
हेलो हेलो।
इसका इसके हाथ में ऑडियंस में किसी को डाउट है तो म्यूट करके रखा अनम्यूट करना जब डाउट है
But this is my screen.
Just drag it to the side. You do actually big it, that will be better. Duplicate screen. Duplicate it is better.
Sir is mirror.
I want one of you to explain to me the meaning of the word FSTTCS. Yeah.
You can ask if it is not clear.
That's the question I'm already expecting. Yeah.
Yes.
I like it. I because I don't understand. But once you understand. Yeah, I mean, it's okay.
It's not equal.
I mean, as long as there's.
आप बात कर वेट कर लो।
Get the yellow card like this. You can get it down.
वही नहीं छोड़ूंगा मैं Oh, you have the clip, my own thing.
This question.
वो आप करने के बाद लाल को सुना आप
Okay. Maybe you can just sit there.
Okay, hi everybody. Welcome to the fairness workshop on the sidelines of FSTTCS. So my name is Umang. I wanted to start by welcoming all of you for coming. I think when we started organizing this workshop, people asked us, how many people are you expecting? We said, well, it'll be us, the speakers. They might bring their students, so maybe 25 people. And then, we had a lot more people registering. So anyway, so thank you for coming. I'll do a longer round of thanks later on, but I just wanted to say thanks to the people of IIIT, particularly the ML Lab. Sujit and his students have done a lot of work. Let me just mention a few words about logistics. If you need help, as I say your name, maybe you can just stand up and so that people can see you. So Sujit, of course, is an organizer of the workshop. Varul, that's Varul. Hi, Varul. Rashid, there he is, already running around. Parth, oh, he went down. See, these people are always so busy. But right, as somebody pointed out, if you don't know whom to look for the people with the longest institute name on the name tags, IIITH, or they also have a yellow tag. Yeah. Great. So yeah, we have 12 speakers lined up. We're looking forward to a lot of very exciting talks. I just wanted to mention that that we've been trying to organize, some kind of game theory related conferences fairly regularly. So we had one at IIT Bombay a few years back on the sidelines of FST over there. Then we had one at Ashoka a couple of years back, and now this one. And we'll try and keep organizing this regularly. So yeah, so we look forward to your continued participation in this as well. So, okay, so I'll stop here. And the first session is going to be chaired by Prajakta. So Prajakta, if you can. Actually, it's not 9 o'clock yet. It's not 10 o'clock yet. So the session starts at 10, right? So, okay. So yeah, maybe we'll take a couple of minutes and then we'll start at 10 o'clock. Oh yeah, there's a clock here which says 10 o'clock. So, right, as you can see, it's going to be an exciting workshop. Okay.
Okay, so we can stick to the IIIT clock and start the session. So our first speaker is Jugal Garg from University of Illinois. Yeah, I welcome Jugal to start the talk. He'll talk about finding fair and efficient allocations.
I think I have this. Thank you, Prajakta, and thanks to the organizers for inviting me and organizing this very nice workshop. So I'll talk about finding fair and efficient allocations. So we will consider the following allocation problem. We have a set n of n agents, and we have set m of m indivisible goods. So indivisible means like one good can be only given to one agent. It cannot be fractionally divided, like a house, cell phone, etc. And each agent I has a valuation function Vi over all subset of items to some positive non-negative real number. And we will assume that the valuation functions are normalized. That means like if you don't give anything, then the valuation is 0, and they are monotone. If you give more items, then it cannot decrease. Like it's like a free disposal. You can throw it if you don't like it. It cannot affect you negatively. So they are monotone. And these are some popular, well-studied valuation functions. I think most of you should be familiar with them. Like additive, where like the valuation from a subset of items is just like sum of the valuation from each individual item, and so on. I'll not go into the details, like probably you are familiar with gross substitute, submodular, subadditive. And the goal is to find a partition of items among these agents and agents such that we get a fair and efficient partition. So the question is, what do we mean by fair and what do we mean by efficient? Any questions about the problem set? Okay. So in this talk, there are three parts. So the first part, we will talk about the efficiency and for efficiency, we want to maximize some welfare function, and we will consider maximum Nash welfare, which is defined as the geometric mean of agents' valuations, or like you just take the product of the valuations and take the mean 1 over n, because there are n agents. It turns out that this is the right welfare notion when we are talking about fair and efficient allocation. It provides interesting trade-off between efficiency and fairness, and it like avoids the extremes of like maximizing social welfare, where like you are not, like it will be very unfair, or like max min fairness or egalitarian welfare, which will be highly inefficient. And it is motivated by Nash bargaining, like you must have learned in the algorithmic game theory course or somewhere. It's the solution of the Nash bargaining problem. And unlike other welfare notions, it provides many interesting properties. So one property is scale freeness. That means that if you scale the valuations of a particular agent by any constant, the output will not change. So it's a scale free. In the second part, we talk about the fairness. We will talk about the fairness. We will not worry about the efficiency, just fairness. And the quintessential fairness notion is like envy freeness, where no one wants to envy anyone. Like I am happy with my allocation, I don't envy your allocation, and so on. But in the discrete setting, because we have individual items, this is not always possible to achieve such a notion. So we will consider envy freeness up to any good, or in short, EFX, which is the closest analog of envy freeness. And we will see what can be done for EFX. And in the third part, we will see like if we can achieve both of them simultaneously. Can we maximize Nash welfare as well as achieve EFX simultaneously? Okay, so let's start with the welfare. So first, the bad news. The maximizing Nash welfare is a very, very hard problem. Like it is NPR even for two agents with identical additive valuations. Like these are like two agents with identical additive valuations. It is NPR. To maximize Nash welfare, there is a very easy reduction from the partition problem. And it is also APX hard, even for restrictive additive valuations, which is like a very special case of additive valuations. And it is hard to approximate within a factor of 1.069. So it's like, it turns out to be a very hard problem, maximizing Nash welfare. But we have good news, like for additive valuations, there is a very, very interesting algorithm given by Cole and Gajdalis in 2015. They provided 2.89 approximation using a concept called spending restricted market equilibrium. Those who are familiar with market equilibrium, it's like Fisher market equilibrium. So it's a variant of Fisher market equilibrium. So they utilize this to get this the first constant factor approximation, and this was improved later, the approximation ratio to 2, and also has been applied to slightly more general valuations than additive. Then another approach came in 2017, Anari et al. They used the real stable polynomials to get a randomized algorithm which provide E approximation to this problem, and that also can be generalized to slightly more general valuations than additive. And finally, Siddharth, Burman, and Rohit, I think those two are here. They gave the best like 1.45 approximation using a different market equilibrium technique, and this is the best factor we know as of today. And this also can be generalized to budget additive separable concave, which is like just slight generalization of additive, not like a gross substituted submodular. And here, like these techniques almost stopped, because like if you want to get like something nice for like gross substitute, submodular, subadditive, then these techniques do not seem to extend. So we need new techniques to design algorithms for more general valuations. So before we go there, let's understand the connection with the matchings. I think it's like because we are just doing the continuous relaxation, and for some modular it becomes like unmanageable. But we will do so differently. Yes, like market equilibrium doesn't make sense, because what is the what is the utility function? Yeah, but it is not clear how to use that, like, yeah. So I'm not saying that this will not work, but we don't know how to make it work. This is the largest class, budget additive separable concave, where like you have a utility limit, like each agent has additive valuations, but some maximum limit, and also like it can go concave. Yeah, so this is the largest class which can be solved using market equilibrium technique.
Even hardness of approximation is like, it's a 1.0, which is.
1.069 is the hardest, like that is like for restricted additive valuations, and it also is for additive and even for this class. So we don't have a better hardness of approximation for this general class. And I will of course like summarize it in the end. And by the way, feel free to answer my questions. Like we don't need to go over everything. Whatever we go over, I think we should make sure that we understand. Any other question? Right? Yes.
Just maybe a follow-up remark to what Siddharth is saying. So the cross substitutes equilibria that have been studied, they are often in the Gaussian utility model, right?
Right. Right.
In this case, we don't have any value.
Yes, yes, that's a good point. That's the reason maybe like we don't know how to use the market. And also gross substitute is difficult to work with because there is no utility function. It's like defined like little through prices. So yeah, we can discuss more about it maybe after the talk. Like
There are like, there's a point that
right,
other sort of.
right. Yeah. So anyway, we have a different technique which will give you like some very nice factors. So okay, so let's understand the connection to matchings. So maximum net welfare is this function, like we want to maximize the product, the geometric mean, right? And if we can take the logarithm of this function, which is like usually we take, and then this is the same function, like you maximize this or maximize the sum of logs, they are the same thing. And just notice one thing is that if m equals n, that means the number of items are same as number of agents, then what is this? You need to give at least one item to every agent, otherwise the product will be 0, right? Because we assume that if you don't give anything to one agent, then his or her utility is 0. So if the number of items are same as number of agents, then everyone has to get exactly one item to get any meaningful number, and which is just like a matching, right? So when m equals n, you can just solve this problem optimally by just doing the max wet matching. But when m is greater than n, which will be usually the case, the number of items are more than the number of agents, then how good is the max wet matching? So this example suggests that like the max wet matching could be very bad. You cannot get rid of a factor of m. So I will not go into this example, but I can explain you later. So when m is bigger than n, then just doing max wet matching can be very bad in terms of approximation factor. But matching can be exploited to get very good factor, and these are the recent developments. So the first development came in 2020, where we obtained n log n factor, which is independent of m for submodular valuations. And then Siddharth, Umang, and we also showed that like for sub-additive valuations, you cannot do better than n. It's a tight factor. Like for sub-additive valuations, n is the tight, and which can be we can achieve that. And then like Lee and Wondrak in 2021 came up like extended their real stable polynomial approach to estimate the welfare value. Like they say that like they say that like if you look at like kind of Redo valuations, or it's like gross substitute valuations. So gross substitute valuations, then you can estimate this factor, the welfare value, within a factor of 6.8. So you will not get an allocation. It will not give you an allocation. It will just tell you that the maximum welfare is like within a factor of 6.8. And then in 2021 we came up with a first constant factor. The constant is 772 for Redo. Redo is like gross substitutes. So we just need like defined by matroids and matchings. So 772 approximation, and then using and then immediately after that, like Lee and Wondrak gave a 380 approximation for submodular, and finally, I'll tell you, like we get a very simple algorithm which give 4 approximation with submodular evaluations. So my aim is to like give you a brief sketch of this algorithm. Okay, so let's start with the first breakthrough, like where we got 3-phase algorithm. So phase 1, we need to find a matching, max weight matching. Just find a max weight matching. So recall that the example which I didn't go over, it can be very bad. You cannot get rid of factor of m. So we cannot commit to allocating these items in the matching to the agents. So we find a matching, we keep these items aside. We are not allocating them. We just find these n items which are like kind of high value items, right? Because max weight matching will keep aside high value items. The rest of the items will be like low value, right? So in the second phase, you forget about the items allocated in the first phase, and you allocate the remaining items using a very simple round robin algorithm. You just use a round robin algorithm to allocate the rest of the items. Now we have done the allocation of these low value items, and then in the third phase, you recompute the matching. But now you have more information because Ri is already given. So whatever you give in the phase 2, that is you are actually giving. In the phase 1, you are just computing n items and keeping them aside. In the phase 2, you just allocate the remaining items using round robin. In the third phase, now you know like how the low value items are allocated. Then you again find a matching using this Ri plus like whatever the items you kept aside. So in the third phase, again you will be giving one item to each agent. But now you have more information, so this may not be the same matching as this one. And we show that like this gives n log n approximation. So you can get rid of factor m. Okay. So next algorithm, we just need to change the phase 2. So this is like 772 approximation for submodular, for Redo evaluations. So we just like, because the round robin was a very simple procedure, right? Very like, we just plug in concave relaxation, because for gross substitute, you can have a concave relaxation. And then we use some sparsification and rounding techniques to get a constant factor approximation for Redo evaluations. So phase 1 and phase 3 remain same. It is just like how you allocate the low value items. So instead of round robin, we now use the concave relaxation. And the Lee and Wondrak did like the natural thing because they wanted to work with the submodular evaluations. So for submodular evaluations, there is no concave relaxations. So they use the multilinear relaxation, and then they utilize the iterated continuous gradient randomized rounding to get a randomized algorithm, which gives 380 approximation for submodular evaluations. So the phase 1 and phase 3 remains the same. Only thing you are doing is that how to allocate the low value items in some nice way. And finally, we realized that, so this paper came up because like Lee and Wondrak and this paper, they have like almost the same approach. Instead of concave relaxation, like they are plugging multilinear extension, right? So we thought that let's merge the papers for the journal version. So of course, like working in 2 groups can be very difficult. So we were like working together for like 1.5 years and keep improving this factor, like 380, like let's say 350, 300. And like, of course, it was still like keep working. And finally, like suddenly we came up with a new approach. So sometimes like working together with 2 different groups can be fruitful. So this is how this is the output of this like collaboration. So so we just plug in the simple local search instead of all these like complicated stuff, and we prove that this gives 4 approximation for submodular evaluations.
Idea for first and second phase like complement each other, but intuitively the point is to get rid of very high value.
Yes, the point is to get rid of very high value items, because you need to know how the low value items are allocated, then only you give the high value items. Very good. Yeah, I think this is the reason for the niche welfare, because like if you don't give the high value items in correctly or appropriately, then it can be very bad. So the main takeaway is that you need to worry about the high value items, and we just took care of high value items by keeping them aside, allocating the low value items, and then finally bringing them back. And so one drawback is that like we can only use the matching, and it will come in the open question that like the problem is that yeah, it only works for the symmetric problem, because in this asymmetric problem, if we know that how to allocate these items, like maybe some agent we want to give 5 items and so on, then probably we can solve the asymmetric version also. Yes.
Does not have any they give you an upper bound. So BI maybe will
Yeah, I think it is just like large market assumption or something like. Yeah, I think it is easier. I think it's already somewhere in some paper. Okay. Yes. Yeah, I'll go back. I'll give you the details. What is the local search? Yes. Yeah, that's a very good question. It doesn't give better than 4 approximation, and we thought about it because like we think that like additive we can get better than 4, but no, it's like it doesn't matter whether you use additive or some modular, we get the same approximation. Very good question. Yes. Maybe better by some more bug, but not, we cannot beat like Burman and Rohit. Yeah, wedge result. Yeah. Output is not guaranteed to be Pareto optimal. Yes. Any other question?
Why don't we just do it twice and like allocate 2 heavy items per agent and then do the local search and then real? Why stop at just 1 heavy item?
Yeah, so I think you can do that, but you will not get better than 4. Yeah. So yeah, you can like you can keep aside as many items as you want, but we don't know how to get better than 4. Yes. And this is, I think, yeah, this is a very good idea, but we don't know how to do that. I see. Yes. Yeah, so here I am assuming that like the evaluations are like given by value oracle. So you, because like you can specify the values and submodel evaluation. So you ask like what is the value for this particular bundle. Like for sub additive, like we cannot do better than an approximation, but Siddharth and others came up with came up with an approach to break this n factor if you have much like a stronger oracle like demand oracle. Okay, any other questions? Okay. So I will give you details of this simple local search. So I think the phase 1 and phase 3 are like straightforward, like what we are doing, keeping n items aside and then rematching them in the third phase. So let's look at the local search. Of course, it is not that simple. Like simple means like you just don't do the local search. The main idea is this: you find the favorite good of each agent in the remaining set. H is the set of items we kept aside in the first phase, and M minus H is the remaining set of items. And you find the favorite good of each agent in this set. So let's say Li is the favorite good of agent I. It can be same for multiple agents, right? Multiple agents may have the same favorite good, right? So what we do, we modified the valuations. So what is the modified valuation? You assume that we have given the favorite item of each agent to that agent. Let's give them. We cannot promise them, but let's give them like just as a thought process. So our valuation is like Vi at S, VIS plus Li, because Li we assume that it's already given. So what is so pretend I already owns their favorite good. Yes, so we will come back to that because we have H to rescue. the phase 1 items are to rescue because, okay, it will come. So what is the property Vi at of empty set is Vi of Li, because if you don't give anything, then each agent still has Li, and using some modularity, the value of any good cannot be more than twice of the empty bundle, right? Because some modularity. No, we are not doing anything. Just pretend. We will come back to that later. We are not doing anything because everyone likes one item. You cannot. They don't like anything else, so you cannot promise. But currently, just pretend. Just defining a new valuation. So just defining a new valuation. So now we do the local search on the new valuation. So what is the local search? Local search is a very simple procedure. You start with any allocation on the new valuation, where like you have given Li to each agent I. You start with any allocation and then you move one item from one agent to another agent if it improves the nest welfare by at least 1 plus epsilon. Very simple procedure, right? Local search. You just need to move one item from one agent, take one item to one agent to another agent if it improves the nest welfare by at least 1 plus epsilon. You keep doing this and you can imagine that this will be just some polynomially many iterations where we will stop and let's say, this is the local search. Here we are completely ignoring the items, the phase 1 items, because phase 1 will only come in phase 3. In phase 2, our worry is on to allocate the remaining items. Now, okay, so I will not go into the lot of proof details, but what we can show is for this modified valuation, we are not very far because let's say S star maximize the nest welfare for these remaining items. So this Ri is the set of items given to agent I in local search. So we are like only constant approximation, but with this modified valuation. Now let's open this modified valuation, what it is saying. So by the way, one thing to note is that local search for the original nest welfare problem can be arbitrarily worse than the optimal solution. You cannot do local search on nest welfare problem, right? Because suppose there are m equals n. You start with any allocation, you will stuck there, right? Because there is no way to move one item from one agent to another agent. So this modified valuation is the key to do the local search. Otherwise, you will be stuck. Even if you try any constant items, you cannot move because m equals n, then whatever allocation you start with, you are stuck. You cannot move anything from anywhere, even like any number of items. So this is important that this modified valuation is important. So now we open this up. So Vi hat is like Vi of Ri plus Li, right? This is just the definition. So we are getting Vi of Ri plus Li is like, and Si star is the maximum nest welfare allocation. And of course, Vi hat is bigger than Vi because Vi hat is bigger than Vi. So we get this relation that like Ri plus Li, if we can give each agent Ri plus Li, then it gives a constant approximation to the maximum nest welfare problem. But the only worry is that Li we cannot promise, right? Because Li could be same for every agent. So now we prove that what we do in the phase 3. So Ri plus Li plus pi I, let's say pi I is the item each agent gets in the phase 3 when you bring back the items from H. So we can show that Ri plus Li plus pi I is also some constant approximation. This is easy. This is like not difficult because like here still we are promising that Ri plus Li is anyway giving constant approximation and like it's just like a nest welfare problem. So if you also again do the rematching for the phase 1 items, so this is an easy lemma. You still have constant approximation. So we are almost done. The only problem is this Li. Only problem is this Li because we cannot give Li. Because Ri we can give, pi I we can give, where to give Li. But the thing is that because an allocation infeasible due to Li's, but yes. Yeah, it is just like you can take epsilon, any small like epsilon m, you can eat up in the epsilon. So don't worry about that. This is just a case analysis. Now in the optimal allocation, if Li is the highest item, the agent I got, then you are giving pi I, which will be, there exists one item which is better than Li. And if something from sigma I is better, then anyway you are giving. So in any case you are giving, so you are not losing a factor of 2. So this is just the idea because Li can be taken care of using the first set of items. So I think start with infeasible allocation. So as I was saying that you need to just have Li and pi I, because there exists pi I which is better than Li for every agent, and that will take care of Li, because you will lose a factor of 2, right, at most, right? If they are getting both Li and pi I, but you are giving pi I, so it's a factor of 2. So this is like just a hand wavy argument. So the key fact is that every agent I, there is a better item we have which we have not allocated, which is better than Li. So we can get 4 approximation using this approach. I think we use some modularity in proving, I think, this thing.
Second step is subarity.
Yeah, I think most of the thing works for subarity. Only one thing only one place we need some modularity, and it should not work for subadditive because of your result. So yeah. Okay, so let me summarize. So this is there are many open questions here, like those who are interested in working on this. So we have still a huge gap between hardness and algorithm. For restricted additive, I showed you 1.069, but the best we can do is 1.45, which is also, I think, best we can do for restricted additive. And of course, additive, we have the same bound. And for some modular, we can only get 1.5819 hardness, but we have only 4 approximation through this algorithm. So there is still a gap. But more interesting problem is the weighted Nash welfare problem. So far we have assumed that all agents are symmetric. We were just doing the symmetric geometric mean, but if they are weighted, if they are weights, like agents may have different entitlement, then we want to maximize this thing, the weighted geometric mean. Vi of xi raised to wi. Now wi is the weight of agent I. And for this, like our algorithm gives only for some cases it is like order and approximation. So the thing is that the hardness is still like 1.069 for additive, but the algorithm we only have order n algorithm. So there is a huge gap, like from a small constant to order n. Even like any sublinear constant we don't know for weighted Nash welfare problem. And like the same approach can be applied there, but the reason is that like the matching only gives one item to each agent. So that is the problem. We don't know how to extend that approach to weighted Nash welfare problem. Okay, so next let's talk about the fairness. Any questions about welfare? Symmetric means like weights are equal. So this wi is, let's say, 1 over n, right? All agents have the same weight. But if you look at the weighted Nash welfare or weighted geometric mean, then we don't know how to approximate it better than order n approximation. Okay. Any other question? Okay. So next is the fairness. So NV freeness, as I said, is like defined as, like we say an allocation X is NV free if every agent for every pair of agent Vi of Xi is at least Vi of Xj, like no one envies anyone, right? Everyone is happy with their allocation, and we cannot guarantee NV freeness. If there is only one item, then only one agent will have it. Then you cannot get NV freeness in very simple instances. So we need to relax it. So the closest analog of NV freeness is NV freeness up to any good. And here the definition. Because like if I don't envy, then that's fine. But if I envy, then if I remove any single item, then my envy should vanish. If that happens, then it's called EFX. If that happens for every pair of agents. So Vi of Xi should be at least Vi of Xj minus G for all G in Xj. Okay. So now the question is like, can we always guarantee EFX? And the answer is we don't know yet. So this is considered fair division's biggest open question, and it seems to be highly non-trivial. So this is the state of art on EFX. So for 2 agents it exists. For 3 agents also it exists. 3 agents with additive evaluations. It exists. and more than 3 agents, we don't know. And because we were not able to make progress on EFX, so people considered various relaxations. So these are the relaxations. So EFX with charity, so means like you don't allocate all the items. So suppose you don't allocate anything, then it is EFX, right? Everyone has nothing. So we want to allocate as many items as we want. So we want to minimize the number of unallocated items. So current best is n minus 2. So we can allocate all the items, but some n minus 2 items, and the partial allocation is EFX. And another like standard relaxation is alpha EFX, where you relax the EFX requirement by multiplicative factor alpha, and currently we know 0.5 EFX sub-additive and 0.61 at EFX additive. And then you can combine both of them, alpha EFX with charity, and then you can get some sublinear bound on the unallocated goods with 1 minus epsilon EFX. So like I'm just showing you these relaxations, like just to like encourage you to work on these problems. Yeah. Yes. These are like, I think all the techniques are algorithmic. We don't know how to prove only existential results, like how to use fixed point theorems and so on. So all of these are algorithmic results. So since I don't have a lot of time, so I'll just focus on the first 2 results. Yes. Okay, yes. So let me focus on this thing. For n equals to, it's a very simple algorithm, divide and choose. You just ask one agent to partition all the items into 2 bundles such that they are almost equal. Like that, like y prime may be better than y, but if you remove any good from y prime, then you prefer y, or you are okay with y. And just think about it, it exists. Like you can also think about a very simple algorithm for additive evaluations. So it's just a simple exercise to check that such a partition exists. Now, once agent 1 partitions, then you ask agent 2 to pick their favorite bundle, like y or y prime. So of course agent 2 is happy because agent 2 is picking the best bundle, and agent 1 is also almost happy, or EFX, because if they get y prime, then they are happy. If y is also almost is EFX. So in any case, like EFX exists for n equals 2. So very simple algorithm, right? For n equals 3, things becomes much more complicated. Just like one more agent and things becomes very complicated. So for n equals 3, so I think I need a concept of NV graph. So those who are not familiar, NV graph is a very popular concept in fair division. So where you create a graph where vertices are the agents, and so let's say these are the agents and these are some allocation, like x6 is the allocation of agent 6, and you put an edge between agent from agent I to agent j. It's a directed graph. If I NV is j, so suppose this is the NV. So if I prefers j's bundle, then you put a directed edge from I to j. So NV graph is a very simple graph, right, of the current allocation. Now, what is one good thing is that there is a cycle in this graph, right, in this particular graph. If there is a cycle, then there is a very easy solution for the cycle, right? Because like you just circulate the bundles along the cycle, right? Because like 4 prefers x6, 6 prefers x5, and so on. So you just circulate the bundle along the cycle. So we can always remove the cycles because we are always making the allocation better. Because the remaining agents who are not part of the cycles are not hurt, and the agents on the cycles are getting better off. So we can always remove the cycles and get a better allocation. So this is like, we can always assume that NV graph is acyclic. If it is cycle, you can just like circulate bundles, and yeah, so it is acyclic. And so the proof goes like this. For 3 agents, we look at the sources in the NV graph. Now there are 3 agents, so there are only 3 vertices. Just 3 agents, right? We only so 3 vertices. So we need to we divide the work in like how many sources are there in the NV graph. So there are 3 possibilities. Either there is 1 source or 2 sources or 3 sources, right? 3 possibilities. So this charity paper already solved the case one. If there is only one source, then you can find a better allocation. You can you can keep making progress. So if you have a partial EFX allocation, partial means like initially you start with empty allocation, no one has anything. But then you can add items to the agents. And then if you have a partial EFX allocation and unallocated good G, and it has only single source in the NV graph, then you can make progress. That means you can find an allocation X prime, which Pareto dominates X. That means like some agents are getting better off and no one is getting worse off. So this is already like given by that charity paper. And we proved that for 3 sources, we can still do the same thing. If there are 3 sources in the NV graph, then we can still make progress. We can find an allocation which Pareto dominates X. But for 2 sources, this does not work. Because there are examples where there's no way you can make progress if the progress measure is Pareto dominance. So we have a partial allocation and we have still some unallocated items and the NV graph has 2 sources, then maybe there is no way to make progress because someone has to be worse off to allocate more items. So then we consider a new potential function, which is lexicographic potential function. And we relabel agents ABC. And then we consider this potential function. So first is the valuation of agent A and then B and C. You fix them a priori, like in the beginning. And then we show that like you can make progress on this lexicographic potential. So like if you are making Pareto dominance, then it is also you are improving lexicographic potential, but it is not true vice versa, right? Because here like you need to maybe like if A is improved, then B may be hurt, right? Which is fine, right? In the lexicographic potential. So this implies that the EFX exists for 3 agents. And we don't know how to do it more than 3 agents because it becomes many cases and it becomes very complicated. Yeah.
This does not say that the lexicographic maximal allocation is EFX, right?
Lexicographic maximum, yeah, it doesn't say that. It's just like an algorithm. Yeah. So it's like for if you look at the NV graph, if there is an algorithm. If it is 1 source, what to do, 3 sources, what to do, 2 sources, what to do, such that we improve the potential. Yes. Yeah. We try to allocate G to some agent and we may also throw away some good back to the unallocated set. Yeah. It's not like a strict progress because you allocate the thing is that like the goal is to improve the potential. Yes, while maintain. Yeah, we always maintain EFX. This is another thing. Throughout, like we start with the empty allocation, we keep maintaining EFX. We never lose EFX because if we lose EFX, we don't know how to fix that. So you keep maintaining EFX and keep improving the potential. So this is the potential. You assign someone agent A, someone B, someone C. So you want to improve this potential. 1 and 3 anyway, you can do Pareto dominance. So this potential. Yeah. No, Pareto dominance implies this. Yeah. But for 2 sources, we cannot get Pareto dominance. So but we can get this one. So only for 2 sources we need to do this lexicography. But we may get 2 sources on some instance. Like I'm not going into the details of the algorithm, but the potential is just you just improve this potential, the lexicographic potential. I give you X, which is EFX. You give me X prime, which improve this potential. No, because like you have X and you want to add more items, right? So maybe you add 1 item, but you may throw out some items. That's okay, right? Because you may be adding a valuable item and you may throw out some non-valuable item to make it EFX. Yes. Okay, so EFX exists for 3 agents. I will be happy to talk to you after, like, yeah, feel free to. This algorithm is pseudo-polynomial. This is also very interesting thing. We don't know if we can compute EFX for 3 agents in polynomial time or what is the hardness. So this is a pseudo-polynomial time algorithm because this potential can take pseudo-polynomial time. Very good questions. So this is like there are so many open questions, right? Like So like improving these bounds. And finally, I want to talk about like what can we do with like can we achieve together maximum net welfare and EFX? And this is the only slide for that one. So we are on time. So Karagianis, Gravin Hwang in 2019 showed existence of partial EFX with two approximate MNW. So like partial EFX means like you are not allocating all the items, but you can achieve two approximation of the maximum net welfare. Yeah. Then like we improved this result to show the for sub-additive existence of complete half EFX with 2 MNW. So what is happening here that we are getting the best EFX guarantee, because for sub-additive half EFX is the best you can get. But together with half EFX, we are also getting good welfare guarantee, 2 MNW. And sir, not polynomial because this is like, yeah, of course. And then like I think Feldman, this recent work, like they improved both these results. So they showed like for additive, they can match the best EFX guarantee, alpha EFX guarantee with very good net welfare approximation. So you can achieve the best fairness guarantee with very good welfare approximation. So you can achieve together, both of them. Okay, so this is my talk. So questions? Yes. Like it's an existential problem, right? So it exists now because of that result. Now the question is, does there exist a polynomial time? Yeah, it could still be polynomial, but the algorithm what we came up with is not polynomial time. It's like pseudo polynomial time. Like we don't have we don't have tight analysis. We don't have an example where like, yeah, we have never tried. We have not tried that. Yes. Yes. And here, like I'm not talking about Pareto optimality. EFX just EFX. You can be very bad in terms of Pareto optimality. Yes, it can be very bad. So like I think a very interesting question you are maybe posing is that can we achieve this charity thing with Pareto optimality? Like you allocate get partial EFX allocation with some items unallocated and also achieve Pareto optimality. Hmm? Yes. Yeah. Like how you define Pareto optimality. But maybe MNW to MNW may be making someone agent for every agent. That is like, yeah, that is a stronger guarantee, right? I see, I see. Right. Any other questions, comments? They're out of time, so maybe I should stop. Thank you.
Yeah, thanks, Jugal. It was a very nice talk. Yeah. We'll begin with the next talk immediately and we'll have a coffee break after this.
There's a talk after this and then.
There is a coffee break in between.
Oh.
So if someone asks question, maybe repeat the question for others to hear.
I do need a, yeah.
Yeah. No, that is after this talk.
No, but,
Talk will be after. Okay, so our next speaker is Nidhi Rathi from Max Planck Institute of Informatics, Saarbrücken. And she will talk about existence and computation of epistemic EFX allocations. Over to you, Nidhi.
Okay. I'm audible? Okay. So good morning to all of you and thank you to Siddharth, Sujit, and Umang for organizing such a wonderful workshop. And I'm happy to be here and give this talk. And also thank you to all the local organizers. Okay, so I'll jump right into my talk. Okay, so I'll talk about fair division because we must. And I'll talk about something known as epistemic EFX allocation. And so Jugal has set up a very nice thing for EFX allocations, and he has shown a lot of work has gone into EFX allocations. And I'll talk about something related to EFX. Okay. So we do know, like we live in a society where a lot of decisions require making such decisions where you need to fairly divide a resource among the people of society. So some of the examples are like there's an inheritance that is to be divided among heirs, and there's a lot of food is donated to food bank, and now it is to be given to charities. Access to rainwater reservoirs has to be granted to farmers, and so on and on. There are many examples, and this has now necessarily led to a formal study of the area, and this is now known as fair division. It has been flourishing for a very long time with many interesting algorithmic and existential problems. And so we'll focus on okay, so the first question to ask when you delve into such an area is, what is fairness as a concept? And then once you decide what is fairness as a concept, you must also now start thinking about how to compute such a fair allocation. And the setup is exactly what Jugal has told us about. So we will have a bunch of agents. They all have valuations over a set of items. And in this talk, throughout the talk, I will assume the items are indivisible in the sense they are discrete in nature, and the item has to be wholly allocated to an agent. And throughout the talk, I'll have agents denoted by I, J, and K. Valuations I'm assuming to be additive, and items would be denoted by G. Okay, and now the overarching goal here is to divide these items among the agents in some fair manner. And so fairness as a concept can be seen to have two interpretations. One is when you have comparative. And what do I mean by comparative? You have allocated, there's a partition of items you have done among n agents, and now what they do is they evaluate their own bundle by comparing the bundles present in the allocation, and that's the comparative notion of fairness. And the most quintessential notion along these lines is that of envy freeness. And I say an allocation is envy free when for all agents I and j. So when I say v subscript I mean the valuations of agent I, and A subscript I is the bundle allocated to agent I. So what do I mean by envy freeness? Whenever an agent is allocated to a bundle, he or she must think that, okay, I've gotten as much as I could have gotten out of this allocation. So VI of AI, this value is at least as high as her value for any other bundle present in that allocation. And then comes fairness notions, which are in absolute terms. So here, what you do is you define some threshold value. Each agent defines her own threshold value according to some definition. And then I say an allocation is fair in those terms if every agent gets a bundle which is of value to her at least as high as that threshold value. And again, the most important or the most well studied, the first one is that of proportionality. And when do I say an allocation is proportional? It should be the value of the bundle to this agent, which is VI of AI. It should be at least as high as the proportional value for the whole set of items present in the problem instance. But sadly, when you talk about discrete items or indivisible goods, unfortunately, envy freeness and proportionality may not exist. And hence, there's been a lot of work along the lines of relaxing these notions. But before that, we must also ask, when is a fairness concept important? It must be fair. At least the community must look that concept as being fair. It should always exist, and it must be efficiently computable. If we achieve all these things, we have somehow achieved the holy grail of fairness notion. And along those lines, the first notion which was introduced for the discrete items was back in 2011 by Budish, when he described or defined a notion that is known as envy freeness up to some item. here what you do is you say a location is EF1. When you look at your own bundle and you look at any other bundle, there may be some NV, but the NV goes away as soon as you remove some item, and hence the term up to some item. So it is EF1. And if that happens for every agent, I say the location is EF1. The very good part about it is it always exists and it can be computed in polynomial time as well. And there are many mechanisms. The draft mechanism is like a round robin algorithm. The NV cycle elimination. You can also achieve EF1 by maximizing your Nash social welfare. So it's very well studied, and it always exists and also can be computed in polynomial time. But yes, sir.
Evaluation may not be additive. Evaluation will not satisfy this.
Additive value, no, it exists for even much higher class of which is called as monotone.
When you're removing the evaluation comes down.
Yes, it does come down. Monotone, yeah. Yes, the NV cycle elimination works for all other monotone valuations. Okay. And then, but it feels there's something wrong about EF1. So if you look at this particular example, there are 3 agents, there are some particular items, a house, Mona Lisa, the paintings and all those things. But what is happening if you look at the second agent, she has gotten, it feels the best out of it because she has also gotten the bungalow and also a necklace. And if you look at the definition of EF1, yes, it is EF1 because let's just focus on the first agent. The first agent can remove the bungalow from the bundle of the second agent and she is EF1 happy. And also the same goes for the third agent. But it feels like she has gotten a lot of it because she got the bungalow. But you're removing the most valuable item and then you're saying, oh, sure, now you're fair. So people in the community felt like we've not still gotten the right notion of fairness. And that's when the Kariganis et al. In 2019 defined the notion of EFX, which is now very well studied and is considered to be the most natural and also one of the strongest definition of fairness you can have for discrete items. And as Jugal has also explained, EFX is now is stronger than EF1, but still a relaxation of NV freeness. And any allocation is EFX when an agent can look at a own bundle and look at any other bundle. She must remove any item in that other bundle, and now the NV must go away. So if you can do for any item in that other bundle, and if it is possible for all the agents, you know that you have achieved EFX. So removing any item must remove the NV as well. So EFX is the notion which has been now very well studied, and but the bad part is we don't know if it exists universally. Even for additive valuations, we don't know. As Jugal has said, we only know the existence for 3 agents having additive valuations. And but it has not stopped us because it's a very interesting notion of fairness. People have worked over and gotten results for identical valuations, ordered valuations when there are 3 agents, and some more relaxations. And then you can also talk about approximations. The best known is for additive valuations 0.618 approximation. You can also do with charity, and many results have been gotten in this particular area. But still, we don't know the existence yet. And hence, it feels like we should maybe explore a little bit out of EFX and see if there is some notion of NV freeness which always exists and can be computed in polynomial time. If we do get something like that, it is worth exploring. So now I'll just shift a gear a little bit right now, and I'll also tell what happens when you relax proportionality. For discrete setting, because again, proportionality does not exist. Again, imagine 1 item and 2 agents. So people have relaxed proportionality, and Budish defined a notion of maximum fair share, where you imagine an agent is cutting or is giving a partition, n partition of the whole items, and then she get to pick last. If you do this thought experiment, that agent, the rational way of going about giving an allocation is to now maximize the minimum valued bundle in that allocation. And that's what your MMS guarantee or the threshold is. So for every agent I, the threshold is now maximizing over all allocations, all possible allocation, you look at the minimum valued bundle she's getting out of that allocation. That is your MMS threshold. And if every agent gets a bundle, which is a value at least as high as MMS, you say it's an MMS fair allocation. And again, this also, unfortunately, it may not exist, but people have focused on achieving very, very good approximation of MMS. And there's a lot of work focused on that aspect as well. And now, so just to summarize the various notions of fairness which has been studied in this line of work, we have EF1. Yes, it always exists. It's very easy to achieve, but somehow it does not feel fair. Then you have EFX. It feels it is the right notion of fairness, but sadly, we don't know if it exists for agents more than 3. And then there is MMS, the threshold-based fairness guarantee. And over there also, it may not exist, but even though it is fair whenever it exists. And the implications also goes like, you have NV freeness, it always implies EFX because it's a relaxation. Then EF1 is further relaxation, and hence that implication also goes through. And you have NV freeness implying proportionality, and again, it implies maximum share. So this is the various notions which are very well studied in this area. And now it feels like there's a need of defining new fairness concept, which not only exists, but can also be computed polynomial time. So now, okay, what kind of knowledge do agents have? In one way, agents can have the knowledge of items and the number of agents. If something like this is there, you have notions like proportionality and MMS, because they just need to know the number of items, the items and the number of agents. Then you get threshold-based guarantees. And if you have the knowledge of the whole allocation also, like the way the bundles are formed, you get a comparative notion of fairness like EFX, EF1, and obviously NV freeness. And now there is this new notion of fairness, which was defined back in 2018 by Aziz et al., where they defined this notion known as epistemic NV freeness. So very informally, it is a relaxation of, yeah. Why should we not? Can you repeat?
Why should we look at knowledge to the agents, not knowledge with respect to someone who is allocating the data?
Yes. But when you talk about comparative or threshold-based notions, I'm just saying the agent need not know the allocation itself. So there are two interpretations of fairness. One where you don't need to know the bundles formed. That's when you get like notions like MMS, proportionality. And one where if they know the bundle as well, you can get notions like EFX and EF1. Yeah. Oh, but for equitable also, it seems it's somewhere in bit. Yeah, we do need to know the whole allocation bit, because for equitable, you need to know I value every bundle equally. So you do know the value, you do know the bundle as well. It's still not comparative. It would be somewhere in between then. Yes. And as you will see, epistemic is also somewhere in between. Yes. Okay. Yeah. So in 2018, Aziz et al. Came up with this new definition of fairness, which is known as epistemic NV freeness. So very informally, you have an allocation and an agent looks at her own bundle. And if she doesn't look at any other bundle, if in her mind there is a reallocation of the bundles, she's not at all touching her own bundle, she's just reallocating the remaining items. If in that new allocation she is NV free, you say that that allocation is epistemic NV free when it happens for all agents. So formally, the allocation, this A1, A2 till AN, where the bundle AI is going to agent I, it is epistemic NV free. For every agent, there exists a reallocation. So now reallocation is depending on the agent. They don't touch their own bundle, so AI remains as is. but there exists some reallocation of the remaining items such that in the new allocation, agent I is not envious of any other bundle. If that is the case, I say that this is an epistemic envy-free allocation. It was proposed back in 2018 by Aziz et al. But again, unfortunately, they may not exist. So now, naturally, the next step going along these lines of epistemic notions, the next step is to now define, maybe take a little help from EFX and now define epistemic EFX notion. So epistemic envy-freeness up to any item. So the definition again goes on a very similar line. And this is a notion which we defined in our recent work, which is, I forgot to tell, it is a joint work with Yanis Karagianis, Jugal Garg, who is here, Eklavya Sharma, student of Jugal, and another postdoc from Frankfurt, Giovanna Varicchio. Okay, so we recently defined this notion of epistemic EFX, where again, look at your allocation, whatever is being defined. You look only at your own bundle. You look at your own bundle and if you're able to reallocate the remaining items such that now in that new allocation, you are EFX happy. That is your EFX constraints are not satisfied. That is, you look at any other new bundle, and if you can remove any item from that bundle, the envy goes away. If that is happening, I say that it is an epistemic EFX. The only difference, you remember the definition of EFX, and then the only difference is now you are saying that every agent, if they are able to reallocate the remaining items, not at all touching their own bundle, if in their head they can rearrange or reallocate the remaining items such that they achieve EFX guarantees for them with the bundle AI, you say it's an epistemic EFX allocation. And MMS? Yeah, I will go into that. Yes. So formally, there's an allocation A1, A2 till AN. I say it is epistemic EFX if for every agent there is a reallocation of the remaining items. So I'm not touching AI. AI is again as is. There's a reallocation of the remaining items such that the EFX condition for this agent I with the bundle AI is now satisfied. That is, for every agent I and J, you can look at the other bundle BJ, and if you can remove any item from that bundle and the envy goes away, you say that it is an epistemic EFX allocation. But if there's any doubt in the definition, I would like to take a question and then stop here, because from now on I will start talking about epistemic EFX. Okay, so now the whole agenda from now on is to convince you all that this is a good notion of fairness. Okay, and now as we also define maximum share value, we can also define minimum EFX value, and we abbreviate this as MXS. So here, an agent looks at all possible allocations where she is EFX happy, the EFX constraints are satisfied, and then you look at the minimum value she is getting across all such EFX happy, all allocations where she is EFX happy. The minimum value is what we call as the threshold MXS, minimum EFX value. Yeah. I will come back to it. I mean, right now I'm just defining, and we will talk about existential and computational questions of these. We don't know if oh no, but for one agent she can compute all the EFX allocation because she can in her mind, because for identical valuations EFX does exist and can be computed. Okay, so now we have two definitions. One is epistemic EFX and one is minimum EFX value fairness. Was there okay, no. Okay, and now the main result for our work is both of these notions are just awesome. Why are they awesome? Because they just not only exist, but can also be computed in polynomial time. For editor, so in my talk, I'll talk about additive evaluations, but we have also extended it to cancelable evaluations. So the main takeaway is to remember the definition of epistemic EFX and to remember that they always exist and can be computed in polynomial time. And the very interesting part over here is we have proved that computing MXS threshold value is NP hard, even for two agents. But even forgetting that, I can compute an MXS allocation. which is not the case with MMS. Computing MMS threshold is also hard, but I mean, first of all, it even may fail to exist, and we don't know how to compute it in polynomial time. Okay, and also there are some open problems. I will talk in the end about it. Say it again. MXS allocation is when you have, so you define this threshold value. An agent looks at all possible allocations where her EFX constraints are satisfied, and then across all such allocations, she looks at the value, the minimum value she's getting out of. That is a threshold, and then allocation is when every agent receives a bundle of value at least as high as her threshold MXS value. The very same, on the similar lines as MMS are defined. Okay. No. Okay. Yes, that's the next up. Yeah.
MXS is defined with respect to
No, with EFX. So you look, and an agent looks at all possible allocations where she is EFX happy.
but that's here for that reason.
Okay, yes, when she gets one item, one bundle of it, because in her mind she is redistributing. Yes, from her mind, and hence the word epistemic as well. Yeah. Okay. Yeah. So we have, okay, yeah. Okay. So this was one of the open problems that if it given an allocation, I'll repeat the question. Given an allocation, can you verify if it is epistemic EFX or not? So for the case when we have chores, we were able to prove that it is NP-hard. But recently, I've just got to know in the morning that Rohit has proved that even for the case of goods, the things which we are discussing, it is also NP-hard. So even verifying is NP-hard, but the interesting part is I can anyhow compute it. And also I give a certificate where an agent can verify that at least the allocation she got is epistemic EFX. Yeah.
Which one is given as input?
Yes, any arbitrary allocation.
One which is not.
Which has some structure. And yes. So yes, here is an allocation where given an arbitrary allocation, it is indeed NP-hard to check if it is epistemic. But I will give you a very special kind of epistemic EFX allocation where the agents can verify that what they have got is actually epistemic EFX. Yeah. Okay. And
That will be epistemic.
for that agent. Oh yeah, yes, okay, yes. Epistemic, yeah, if you give EFX, it's definitely epistemic as well. I don't know what happened. Yeah, it's all good. Yeah. Okay. So these are the notion of fairness which always exists and can be computed in polynomial time. So when we were defining these notions, what we had in mind was to have just a fairness notion which always exists. But fortunately, we also got polynomial time computability along with it. Okay, any other questions till now? Okay, I'll move on. Okay, so now just to understand what is the geometry of fairness properties we have is the green ones, which are the ones which are already known, and the red ones are the ones which we have proved in this work. So you have NV freeness. It does obviously imply EFX because it's a relaxation, and epistemic EFX is the further relaxation. But the interesting property here is MMS allocation also implies epistemic EFX, and that's how a new notion fits into the realm of all the previously defined notions. So okay, so the important implication here is MMS allocation implying epistemic EFX, and epistemic EFX implies MXS is a simple one, which I would not go into details right now because yeah, from now on I will focus on epistemic EFX. Yeah. Okay. Okay, so now what I'll do is there are two parts to my remaining of the talk. First, I will prove that an MMS allocation is always an epistemic EFX allocation, and then I will give you an algorithm proving or achieving an epistemic EFX allocation, and hence also proving its existence. Okay. So let's start with MMS implying epistemic EFX. Okay. So what do? So you consider any arbitrary MMS allocation A, and then you partition the agents different than I into 3 groups. Okay. So now I'm focusing on one agent I, and I'll prove that in this allocation, in this MMS allocation, she is able to reallocate the different or the remaining items in a way that she is now EFX happy in this new imagined allocation. Okay. So now the first set of agents agent I is looking is, now I'm fixing one agent I and defining 3 groups. The first are the agents J against whom agent I is not EFX happy. So even after so there exists some item J or G in this bundle AJ of whose removal does not remove the NV. So the block or the group H consists of those agents J against whom agent I is not EFX happy. L consists of agents J whom agent I does not have any NV. So this is like a good group. There's no NV at all to begin with. And then there is this third group, the remaining agents whom agent I may envy, but she's EFX happy against those bundles. So there are these 3 set of partitions agent I does for the remaining agents. And now what is the process I'm doing? It's a very simple proof. Yeah. So as long as there exists some agent J1 in H, so the whole idea is to make or to reallocate the remaining items such that the group H becomes empty. Because if that happens, what I'm left is either there's no NV or there is NV, but there is no EFX NV, and that's it. So I need to reallocate the remaining items such that in that new bundle or new allocation, the group H is now empty. Okay. So what am I doing? The process is very simple. As long as there does exist such an agent J1 in H and there is an agent J2 in L where there is no NV, it's a very safe agent. What you do is you move an item G in this bundle AJ1 or move an item which is of minimum value to agent I and you move it to bundle AJ2. And I will now describe this process pictorially. What is happening is there is this Vi of AI. This is the MMS threshold value. And because we started with an MMS allocation. And now what is happening is there are 3 groups. There's a group L, which there is no NV against. I'm all looking from the perspective of agent I. There's group M, against whom agent I is EFX happy. And then finally there comes the group H, against whom she is not EFX happy. So group H is the danger one. Group M is, yes, it's always okay. And group L is the safest one because there's not even any NV to begin with. Yes. Okay, yes. There is no NV because I have a bundle of value which is at least as high as your as high as my value for your bundle. So there's no NV. But I say I'm EFX happy against you when I satisfy the EFX constraint in the way that I can remove any item in your bundle and the NV goes away. Yeah. Yes. Green bar, for example, yes, it is EFX happy because and I've arranged these items according to the according to decreasing values with respect to agent I. So if you remove the minimum valued item, the NV goes away. And then comes the danger red agents, where if you remove the minimum valued item, the NV still persists. And I can do that because right now I'm in the realm of edit evaluations. Okay, so now what I do is I do this simple trick. What I have to do is to exhaust or to make the red group empty. So as long as there is some agent, I pick the minimum valued item from that bundle and I move that item to a blue agent bundle. And I do this process. I keep doing. It's possible that it becomes green and now I'm happy. If, as soon as it becomes green in the way that now agent I is EFX happy against that bundle, I stop because that's all I want. And do note that I am indeed rearranging the remaining items. And then finally, the process goes on. And if we are lucky, what we will end up is all the agents are either blue is also okay, or they're all green. That is, I have given you a rearrangement where this agent I with her own bundle AI is now EFX happy. But why does it always happen? Okay, so now, yes. Yes. They can also become red. Yes. I'm just showing the good part. I will now prove you why, even if that happens, I'm okay. Yeah. Some question? Okay.
Just argue that if you are MMM,
Yes.
there is a limit partition of the remaining goods. So M minus all the goods minus AI.
Yes.
Among N minus 1 agent.
Yeah.
That is a value less than the correct. Doesn't that give?
Yeah, that is all. Yes.
That gives.
If it is lesser than the MMS value, then yes.
I mean, they're reducing the set of goods.
Yes. Yes.
AI.
Yeah.
You're reducing the number of agents by one.
Yes.
But notice that what you have removed, let's say is more than the MMS value.
Yeah.
So if you can say find a bundles that are more than the MMS, the original MMS,
yeah,
you could have just started that as the original. So and add this. So I mean, sorry, MMS is the lowest bundle. It is. But the other bundles can have more than the MMS. Which is fine, but like you still have increase, right? For
this agent.
It will go down. My claim is that it will always go down. We can check that. But if that's the case, then the
yeah, if that's the case, if for the remaining, okay, so what you're doing is for the remaining items.
All the goods minus AI.
Yeah.
And look at the MMS value, but now define an
N minus, which would be lower.
My claim is not obvious, but
okay. Maybe, yeah, okay. Yeah. We'll discuss it later. I would like to see that idea as well. Okay, so now what is happening is there's this group H. It can, when you're doing this process of moving the lowest valued item from group H to group blue, it can either become group H or can become group M. That is, you have achieved EFX happiness, or what can happen is there is this group L to whom you are moving the items. It can stay group L. It can become EFX happy group, or they might now be a danger group. But what is happening is the value of the minimum valued bundle in this reallocation is always increasing, and hence I have a potential. So what you asked is possible, but it's okay. Eventually, what will happen is either the group L or group H becomes empty. If group H becomes empty, I'm happy, I'm done. The redistribution now I have is indeed an EFX happy distribution. Again, all with respect to agent I. But what happens if group H is not empty? There is some danger agent, but group L is gone. The group of the safe agents where I was doing this move. What happens there? If such what I'll show in the next slide is if such a thing happens, if you assume such a thing, we do achieve a contradiction to MMS. So what happens over there? Let's say something like this is happening. The group L, the safe place to move the items, is gone, but there's still remaining a group, the red group, against whom there is EFX unhappiness. So what you do here is, if something like this is happening, you just move that minimum valued item to agent I's bundle, and now which has just improved or increased the MMS value, MMS threshold value for agent I. And that is a contradiction to the definition of MMS itself. Because now what I've done is I've increased the value of the minimum valued bundle in this allocation. So what you started was not MMS threshold value for agent I. And that's it. So, yeah. So what? Yeah, we'll discuss later. Okay. So that's it. You start with any MMS allocation, it will be an epistemic EFX allocation in the sense that every agent will be able to reallocate the remaining items in a way that she achieves her EFX constraints. Okay. So that's it. That's where the new notion of epistemic EFX lies. MMS implies epistemic EFX. And now, okay, so this is again the geometry of fairness properties. Again, the everything below the dotted horizontal line are all the ones in absolute terms. All the above are comparative notions. All the one to the left of the diagonal are the ones which may not exist. But the good part is all the ones which are towards the right, which we just defined, they always exist and can also be computed in polynomial time. Okay, now I come to the main part of my talk, which is I'll give you an algorithm that computes an epistemic EFX allocation, and also it will be MXS. I'll not now talk about MXS because epistemic EFX does imply MXS. Okay, so the algorithm is very neat. There's just 3 steps to it, and also these steps are already defined somewhere else. We're just accumulating all those 3 steps and seeing that already defined algorithms can also do something more. So step 1 is you enumerate these items. Let's say these items are G1, G2 till Gm, and you redistribute the values so that now each agent has a jth highest value for item J, Gj. So what am I doing is I'm creating an ordered instance from the given original instance. So whatever, let's say it's 5, 2, 6, 1. So what I'll do is now just do 6, 5, 2, 1. That's all I'm doing. I'm just reordering so that it becomes an ordered instance. I know I am distorting the valuations, but I'll come back to it. First step is given any instance, I create an ordered instance out of it. And then I know that whenever in this new instance, which is an ordered valuation instance, we know from previous work that you can indeed compute an EFX allocation for this ordered instance by running an NV cycle elimination. So you do that. And now what you do is you redistribute the items to the bundles. How do you do that? So for each J or for each item J 1 to M, the agent who currently has item Gj in this EFX allocation for the ordered instance, that particular agent is asked to now pick her best available item. And I'll describe the whole algorithm again by giving an example if it's not clear at this point. But you do this redistribution again, and that's it. That redistribution I'll prove is indeed epistemic EFX. But why is it happening? Let's look at an example. You have, again, let's say these same 3 agents and some 5 items to allocate. And these are the valuations in the original instance. What you do is now you redistribute the values. So do note, let's just focus on the first agent. The valuations were for the first item 500, then 600, and so on and on. But what I'll do is I just reorder these valuations so that it is in decreasing. So I now have 600, 500, 4, and 300, and then 200. And I do that for all agents. So from the given original instance, I have now created an ordered instance. And now I know that this is not the right valuations, but now I will consider these items not as an item, but I'll consider them as a voucher. So this is the first voucher, second and third and so on. However many items were there, now there are however many vouchers. Now I have an ordered instance, and whenever you have an ordered instance, you can easily compute an EFX allocation via an NV cycle elimination, and that's what I'll do. I'll do the NV cycle elimination, and I'll not go into the details of what NV cycle elimination is, but okay, so the first agent gets it. Whoever is the source, whoever does not envy anyone in the current partial allocation gets the turn to pick an item, and if there are cycles, you resolve the cycles. But okay, so the NV cycle elimination happens, and now there is a cycle in the sense that the agent 1 does want to have now agent 3's bundle because it's a value 700 to him, and then agent 3 rather would have agent 1's bundle, which is a value 900 to him, which is higher than higher than his current value. So you swap the bundles, and then you continue again. And okay, so now doing an NV cycle elimination on this ordered instance, you get an EFX allocation for this ordered instance. What the best part of it is, this is enough to show that this is indeed, when you do the redistribution again, it will give you an epistemic EFX allocation. With this allocation is a certificate. Okay, so now what is happening is I create a picking sequence via these vouchers. Every agent gets a voucher. Which voucher he is getting? Agent 1 gets the voucher number 3 and 4 because that's the items he picked in the NV cycle elimination, and so on and on. Agent 2 has voucher number 2, and agent 3 has vouchers 1 and 5. Now you create a picking sequence in the way that whoever has voucher number 1 comes to pick first. Whoever has voucher number 2 goes on the second position, and now agent 3 has vouchers 3 and 4. He comes in third and fourth position, redeems the voucher, and picks the item. And how is the now you go back to your original instance and you do this picking sequence. You implement this picking sequence, and agents come and pick the best available item while redeeming the voucher they have. And that's the last and the final step. So you redistribute the items in a way that, okay, now this is again the original instance. Agent number 1 comes, redeems a voucher, picks the item best available to him, which is the first item right now. Agent 2 comes, it's the second item for her. Then 3 comes, it's the fourth item. He picks it up and then also redeems the next voucher, which is fourth voucher. And finally, it's agent 3, which redeems the last voucher and picks the available item for him. So what is happening when something like this happens is, note that whatever they are getting in this allocation is at least as high as they were getting previously. And this is item by item. And so note that this was the allocation they had after solving the NV cycle elimination. But because now agent I is, or let's say the third agent is getting voucher number 1 and voucher number 3, he knows that he'll at least get the item which is the best valued and the third best valued item. And if that is happening, I know that there is indeed a redistribution of the remaining items, even though he's getting 900 and 200 in the final allocation, there is indeed a redistribution even when he was getting items of value 900 and 100. And that's it. So in the step 3, what is happening is agent I is EFX happy with the modified or the ordered instance valuations. But when you do the redistribution again, agent I can be happier with the items with respect to their real values. And when they are happier, I know that the EFX allocation I had at step 2 becomes a certificate or epistemic EFX certificate for that agent to prove that whatever he had at the end is indeed epistemic EFX for her. And that's it. Yeah. Any doubt in the process or the algorithm? Because whatever they are getting at the end is at least as high as what they were getting at step 2, which was an EFX allocation in the ordered instance. Yes. Having a, okay, yes. Okay, maybe I can just go here. So this was the end result or the allocation you get from NV cycle elimination. Whoever gets item 1 or the voucher 1 goes at first position in step 3 to pick her best available item. Whoever has voucher number 2 goes to pick and redeem the second voucher, goes to pick the best available item to her, and so on and on. The vouchers or the picking sequence is created and dictated by the vouchers they have. Yes, they do. He does get to pick twice in a row, the third and the fourth time. Yes, which means he will definitely get an item which is at least the third highest and the fourth highest to her. But in reality, he can maybe also get something higher because it may not have been picked before. And that is the reason whatever he gets in the final allocation, in her mind, she can reallocate the remaining items, which is indeed, which makes her constraints, the EFX constraint satisfied. And that's it. This is the 2/3. Yeah, yeah. Yeah. Yes, 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 yes. Okay. Yeah. You solve. Okay. I was going back. Okay. So now the final algorithm is step 1, you create an ordered instance. Step 2, you run. Now, since you have an ordered instance, you can indeed run an NV cycle elimination and create an EFX allocation for the ordered instance. And step 3 is now redistributing the items with respect to the original instance, where the agent who currently has item Gj or the voucher J picks at the turn J and picks the best available item to her. And I know that whatever they'll get is at least as high as what they're getting out of step 2. And the items they were getting in step 2, that only was enough to make them EFX happy, which means in step 3 also there does exist a location which is exactly the one coming from step 2, which will make them epistemic EFX happy. And that's it. It yields an epistemic EFX allocation and it can be computed in polynomial time. And it obviously hence exists as well. Okay, so the takeaway message is EFX is still a very important and interesting property and a fairness notion, and we must further explore it. But meanwhile, in parallel, it might be useful to explore other notions of fairness, and especially the ones related to EFX and like epistemic EFX and MXS. And the main result of our work is both of them, epistemic EFX and MXS, can be computed in polynomial time, and we can reconsider existing algorithms because they may give something more. And finally, there are many open problems in this direction. One of them is given an arbitrary allocation, is it easy to verify if it's an epistemic EFX, which is now recently solved by Rohit. Given an arbitrary epistemic EFX, given an arbitrary allocation, it is indeed NP hard to decide if it's epistemic EFX. But nonetheless, I can still give you an epistemic EFX allocation and give a certificate to verify if it's EFX, epistemic EFX. And now one can further explore for non-additive valuations, which would be very interesting. And one of my favorite problems right now is proving the existence of simultaneous existence of epistemic EFX and EF1, and also proving if they are compatible with efficiency notion as Pareto optimality and such. And one can also look at price of these fairness notions as well. And yeah, thank you. Oh, yes, yes. No, I mean, not yet. We've been that. So we thought for getting epistemic EFX plus EF1, we do need something more. And we are trying many new algorithms, but none is working right now. Yeah. 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 Yes.
Are there any more questions?
Maybe we can take it to the coffee break because now Siddharth is. Yeah. Yeah. No, we'll take it outside. Yeah. Yeah. Thank you.
Okay, so thank you, Nidhi, and we'll meet after coffee break.
What else? Display settings. Mirror. It was mirroring. Is this
Yeah, it
is the right? Yeah, yeah. Done, right? Okay. Because oh, I don't have the. I think here, right? Hopefully. Okay. I don't know. Identifying your keyboard. Yeah. Okay. Okay.
I don't think so.
Maybe I will just leave this.
I think.
Yeah, I will just use this. I need to stay close to them. Yeah, that's not. Yeah, I'll change it. Okay. Yeah.
Yeah, so welcome to the last talk of this session. This talk will be by Ganesh Galme from IIT Hyderabad. And the talk is about a discrete and bounded locally NV-free cake division protocol for tree graphs.
Thank you, Pratik. Okay, so this is a, can you hear me at the back? Okay, this is a joint work with Jin, Yuka, and Nidhi. Nidhi is in the audience. She was the previous speaker. So let's get into the problem statement. So we have n agents, and we have a cake. Cake is represented by an interval 0, 1. The problem is to divide this cake or find a partition of the cake so that no agent envies the other agent. Envy freeness we have seen in terms of the indivisible goods. This is a natural. I think the predates the indivisible goods case. This is the notion is similar. No agent I envies, or no agent I prefers to have the bundle or the pieces of the agent, any other agent J. Right? So that's the envy freeness. I'll go quickly over the over these slides because it has been it's repeated at least twice. The valuation functions are additive, non-atomic. Valuation function is over. It's a it's a Borel measure. It's additive, non-atomic, and normalized to 0, 1. Now the problem is this: given n agents and a cake, does there always exist an NV pre-allocation? Does there exist an allocation of does there exist a partition of this 0, 1 interval such that if you give AI the piece AI to agent I is happy with that relative to the pieces received by the other agents? It turns out that the answer to this question is yes. However, we do not have an efficient way to find the NV free allocation. Right? So we need to formalize a few things here. What do you mean by efficiency in this case? Right? One way is to I think the most famous one is a Robertson Web query model, which counts the number of queries. There are two types of queries in this model, which count and we evaluate algorithms based on the number of queries it makes. Okay, it's a discrete protocol. So the two types of queries are the natural ones: the cut query, which basically given a subinterval xy and a value alpha between 0 and 1, it returns z, which is between x and y, such that the interval's valuation of agent I over the interval xz is alpha times its valuation over xy, right? And that's where we use non-atomic property of the this thing also. So such a z always exists, and the cut query basically gives us such a z. Eval query is similarly given an interval, it gives you agent I's valuation for that interval. Okay, so the algorithm essentially makes bunch of eval queries and cut queries over time, and we want to find out the most efficient algorithm, the algorithm that requires least number of cut and eval queries. Sometimes we don't distinguish between these two, and then we talk about only Robertson web queries. Okay, but wherever possible, we'll try to distinguish between cut queries and eval queries. Some of the classical results for two agents, it is a straightforward solution, right? When n is equal to 2, first agent cuts the cake into two, whatever he feels, two equal parts, and the second agent picks the piece, one out of the two. And it is very easy to see that this allocation or this procedure is NV free. Right? First person has no reason to envy the second one, because according to the first agent, he has cut the cake into two equal pieces. He doesn't mind which one is picked by the second agent, whereas the second agent picks his favorite, so he doesn't envy the first agent as well. The NV-free protocol for 3 agents was given by Selfridge and Conway in 1950s. This protocol requires 5 cuts and I think some 8 or so eval queries. Okay, under Robertson web model. Though Robertson web model came later, but this was the discrete protocol that was proposed in 50s, requiring some reasonable amount of queries. Okay, for 4 agents, the problem gets little trickier than the 3 agents. So I'll not go into the details of Selfridge Conway. It is kind of out there. So 4 agents gets a little trickier. The problem is that now we have multiple NV comparisons to deal with. Right? All pairs of agents need to, we need to remove NV from all pairs of agents. Okay, so the first work on this is by Aziz and Mackenzie after their work, immediately after their, or maybe sorry, immediately before So immediately after this work, they presented another paper which gives you the solution for n agents. Okay, so this is similar times. For 4 agents, they find a NV-free allocation in around 600 or so queries in total. All right. Amanatidis later optimized this protocol and then reduced the query complexity from around 600 to, I think, 170-ish queries. Some 75 or 76 cuts and rest of them eval queries. Okay, so right. So let me mention the for general n value, the best known algorithm so far, though there is at least one work which kind of contests this, but the best known protocol so far is at best is the finite time protocol. Is the only known protocol which stops in some finite time. It has a tower of 6n query complexity. Well, the only good thing about this is that it stops, yeah, not in reasonable time in any way. Okay, so yes. So what about the other side of the story? The lower bound is disappointingly low. Right? So it doesn't scale. It's not even exponential. The lower bound is just omega n squared. Though there is and it's not I don't believe it's because of the lack of effort, but getting lower bounds in these kind of settings is much harder. Okay. Okay, and this is also this is Procaccia's result from 2009. Now to kind of address the gap, which is a huge gap, like super exponential gap. Let us and there are multiple other works who also do this. Let us try to identify some easy instances and see if these easy instances admit polynomial time, or at least, you know, not that exponential, not super exponential, but reasonable query complexity protocols. So yeah, so here we look at one such specialized special case, which is finding locally NV-free allocations. So in what do we mean locally? So we are given a graph whose vertices are the agents, and the edges of this graph, this is a undirected graph. So the edges of this undirected graph represents some NV restriction. It could be a social graph where agents only care about their neighbors allocation and not any other agents allocation. Okay. Or maybe some other social connections. Maybe we only envy our neighbors and not others, right? And so on. So now the problem of local NV freeness is just you restrict the NV comparison to between the neighbors. Okay, you don't look at all the pairs and choose to. You look at only those which are neighbors of a given agent. Okay. Well, one good property, and it is very easy to see, is that given a graph, you look at the subgraph, and an NV-free allocation on a graph is also NV-free on any of its subgraph. It's so which means that if you find an NV-free allocation on a complete graph, for example, Aziz and Mackenzie's protocol is also NV-free for any graph. Now, the problem is, can we specialize this so can we find algorithms that specialize for certain smaller class of graphs? And of course, the goal is to improve on the query complexity. That's it. I hope this is clear. So, right. So let's get rid of some of the trivial examples. Right? So for instance, let's say 3 agents on a line. This admits a trivial protocol. It's agent 2 cuts, agent 1 and 3 pick in any order they like, and this is trivially envy free, right? Locally envy free. Similarly, the star graph, the center agent cuts, all the other agents pick in any order, and then it is envy free, locally envy free. So this is our first non-trivial small graph, which we will kind of use as you know, we'll generalize this to kind of more general cases, more general graphs. Okay, so let's number the agents from left to right in increasing order, and let's try to find out. So agents 2 and 3 have symmetric roles. So let's say that our agent 3 is the cutter. So this protocol works in 2 phases, equaling phase and the trimming phase and equaling phase. In the first phase, that is the trimming phase, the designated cutter, so all our protocols, this included, will have one designated cutter. Okay. Of course, other agents also may cut on the piece on the cake, but this designated cutter will cut whatever residue or the entire cake, whatever residue is there, into n equal pieces. So whichever agent cuts the residue into n equal pieces, we call that as the cutter agent. So agent 3 here is the cutter agent. Agent 3 in the trimming phase, the first phase, agent 3 cuts the cake into 4 equal pieces according to her. Agent 4 selects her favorite piece. Agent 2 selects her top 2 pieces. So there are 3 pieces left. Agent 2 selects top 2 pieces among these 3 and trims the largest piece to make it equal to the second largest piece. Right? And there is some leftover, some trimming is left, and that trimming is again, that trimmed part is again given to the agent 3, the designated cutter. And in the next phase, designated cutter also cuts this trimmed part, this trimming, into 4 equal pieces. Okay. In phase 1, we get some trimming and we get a partition, basically not a full partition. We also get 4 pieces. So these are the pieces. I don't think this is working. So P1, P2, P3, P4. And this picture, let's only look at the left hand side of left hand side of this. This picture represents agent 2's perspective. Okay, so agent 2 looks at the pieces and thinks, well, I don't care about P4 because I'm not connected to agent 4. Between P1, P2, and P3, though these 3 are equal in agent 3's eyes, agent 2 might have different valuations for these. Agent 2 has picked his 2 favorite pieces, that is P1 and P2, in step, what is that? Step 3, right? And then agent 2 has made the larger piece equal to the second largest piece. So the red part there, T, is the trimming that is left. Well, in the next phase, again, agent 3 cuts the cake into 4 equal pieces according to her. And the same thing happens. The agent 4 selects her favorite piece. Agent 2 selects top 2 pieces among the 3 leftover pieces and make the larger piece equal to the second largest piece. So there is the difference between what happens in the trimming phase and the equaling phase. And the difference is that this part is trimmed and given to 3. Here there is no leftover. There is no trimming left after the equaling phase. Okay. Well, our claim is that this is envy free. The allocation you get. So you bundle these pieces in certain manner. I'll come back to this. But this way of bundling gives us the NV-free allocation of the K, locally NV-free allocation of the K. Right? That's the claim. First, let's look at agent 4. Agent 4 gets to pick the piece from in both the phases first. So agent 4 does not envy agent 3. There is no envy between agent 3 and 4 because agent 4 does not get anything larger than what is equal according to 3. Similarly, now let's see if there is any envy between 2 and 3. 2 gets to pick his top 2 favorite pieces from 3 pieces, right? So agent 3 gets unspoiled pieces, P3 and T3, right? P3 and T3. According to agent 3, all these pieces are equal unless they are, trimmed in later parts. Agent 2 does not envy agent 3. Well, agent 3, let's see, agent 3 does not envy agent 2 because the way we have bundled these two, B1 and B2, right? So we have added the trimmed part, P1 prime, in phase 1 with the part T2, the trimming from the first phase that was added on, right? Something was added on this trimmed part. So, and the second one is that this is the trimmed part from phase 2 and this is unspoiled from phase 1. So this T2 prime can at most be equal to T. So what is added on could at most can make up P1. B1 can be at most P1. So, and he already got P3, which is equal to P1. So 3 will not envy 2. Similarly, 2 will not envy 3 because 2 has got to pick his largest 2 pieces and then there is only some trimming, which again he gets some additional bonus in the second round. So 2 does not envy 3. 1 gets to pick between B1 and B2. So this is how the allocation happens. And 1 is not connected to 3 and 4, and 1 only cares about what 2 gets. So he picks before he gets to pick, and so 1 does not envy 2 as well. And similarly, there is no envy between 2 and 1 because
So I'm looking at agent 3.
yes.
Universal cutter. P3 is the same as P2, fine.
Yes.
Now, but you are adding something on to P2, which is part of T. Right. So I'm looking at B2 and P3. So
Right.
P3 is equal to T2, but T3 can be less than T1 prime.
So, right. So P3 is equal to P2. Okay. And T3 is so is T3 is equal to T1. So T1 prime is less. Right. So that's why 3 does not envy 2, irrespective of what 2 gets. The 2 will get either B1 or B2. So now we have seen that this does not envy under B2. It will also not envy. So this is because of the fact that we have clubbed these 2 pieces in a cross manner. Right. Yeah. Any questions on this protocol? So this protocol is relatively easy. I must mention here that this was independently discovered by Prokashya and his group as well. Well, now let us try to generalize this. Let us go from 4 agents on a line. Let's get most out of this trick, right? So let's go from 4 agents on a line to, let's say, 5 agents on a line. 5 agents on a line is an easy generalization because most of the action happens to all of the action happens to the left of agent 3. Right? Agent 4 is kind of a dummy who picks his piece and goes away. So now you add one more agent to the right, and similar protocol with there will be 2 trimmings and so on, but with some simple tricks, you can generalize this to 5 agents on line. Right? So for 5 agents, we have shown that we show that with 18 cuts or so, 18 or so cuts, we can get NV free allocation. Right? This one needs 8 cuts. Okay. Okay. So now let's look at 5 agents on a line, and let's try to further generalize this to n agents case, where if you ignore all the nodes in between and look at the 5 agents here. So we're kind of adding more nodes to the at multiple places. Okay. So this is n agents case where we're restricting the depth of the graph, depth of the tree. We're still considering acyclic graphs. And later on, we'll discuss the problems arising in the cyclic case. Okay, we believe that the cyclic case is the hardest. I mean, if we crack the cyclic case, it'll give more insight into the general problem as well, like the classical problem as well. However, we're still restricting now to the acyclic case. Okay, so as I said earlier, we have a designated cutter. Even in this case, we have a designated cutter, which is the root agent. And we partition, so D is the set of neighbors of the root agent. We partition this set into 2. Is it visible? So, okay. So the first TR, the set TR represents the set of trimmer agents. In our 4 agents case, agent 2 was the trimmer agent. And we'll also maintain the set of equalizers, which is just those who are not trimmers. And we'll initialize the set of all the set of neighbors of the root agent to be trimmers. Okay, all of them are initially trimmers. Right. So for now, let's ignore this term, the first constant term. It's a property of the graph that is given to us. Li here is the number of leaf agents that are connected to the neighbors of this neighbors of the root. Okay, these are basically the leaf agents, but we can have some leaf agents that are directly connected to the root. Except those, these are all the leaf agents for I. Okay, so our goal is to achieve a domination condition, which is, if we ignore this term, minimum term, for a bit, what we're trying to do is that we're trying to find out an allocation A such that in the eyes of the designated cutter, that is the root agent, whatever root agent gets, that is AR, is his piece, is and the difference between what he gets and all the allocations. So AK of superscript I, this is the, so if we ignore this so subscript, this is the set of all pieces selected by ith neighbor of the root agent. Okay. So each agent picks multiple pieces. In our 4 agents case, agent 2 selected 2 pieces, one for himself and maybe others for his children. Yeah, not neighbors, the children's. Yeah. And then from that, you look at each one of these, and each of these pieces have to be the difference between the valuation of, this should be R here, VI is a typo. So in the root agent's eyes, there is enough difference in valuation from any of the other piece and the piece that he receives. Okay. Oh, K is just a running index of. So AI is the set of all pieces chosen by the ith child of this. Right. And this should happen for all K. Right. Then we say that R, that is the root agent, dominates I. Okay. And when every agent dominates, when the root agent dominates every other agent, then it is easier to, I mean, it's straightforward to get the envy-free solution, locally envy-free solution for dep2 tree. Okay, so here's a protocol. Remember that the set of trimmers is the set D initially. So what we do is we decrease this set of trimmers over time. Okay. Our designated cutter, the root agent, cuts the cake into n equal pieces. Then each agent I, which is the neighbor of the root agent, selects Li plus 1 pieces, one for himself or herself, and Li for its children. Right? They have ith agent has Li children, and then each agent in the trimming phase. So there is no two distinct phases. The agents first are trimmers for few rounds, and then they become equalizers. They equalize the agent, equalize the pieces. So each agent I in the trimming set trims the pieces to make them equal to the lowest valued piece, and they collect all the trimming together, and then you have a set of pieces that are of equal value to agent I. Right. So there is at least one untrimmed piece there, the lowest valued piece, at least one untrimmed piece. What you do is you collect all those in multiple rounds. You will have multiple, I mean, one each, at least one each in each round. You collect all those untrimmed pieces into one bundle. Okay, so that we call that 0, right? And then trimmed pieces are, so you have some trimmed pieces. You collect all the trimming aside, keep it aside, and look at the trimmed pieces. The trimmed pieces are allocated to maximize the valuation difference according to the root agent. You ask root agent how much you value these pieces that are trimmed by agent I, and you look at the least valued trimmed piece and the largest valued allocation so far, partial allocation so far, and you match them. Okay? You add the least valued piece to the largest valued allocation. This is to get the domination quickly. Okay, and then you check the domination condition, and if the domination is achieved for some agent, you remove that agent from the set of trimmer agents. Okay, for all those agents which are not trimmers, these are equalizers. What you do is you just simply equalize. You get Li plus these agents, pick Li plus 1 pieces and make them equal. Okay. Yeah, and then to make them equal, also there is one catch here. You need to add the piece that is some stuff is removed from to the special bundle that we're creating. You don't add the piece which was added on as a part of equalizing procedure. So as a part of equalizing procedure, you trim some pieces and you add that stuff into another, right? You only have to have trimmed piece to add in this special bundle A0. Okay, so that's one catch. And subject to that, you just arbitrarily assign other parts or other pieces to a partial bundle that you are creating. And then finally, leaf agents pick their favorite pieces. The leftover piece go to the agent I for all I in D. So to show that, okay, are there any questions in the algorithm that right? So there is a designated cutter. It has a bunch of neighbors. Neighbors pick pieces for himself. No, Li is the set of the Li is the children of ith neighbor of the root agent, right? Only its children. So yeah, if you look at here, so for example, agent 3, A3 has this L3 number of children. Yes, yes, Li will be 0. And for 1, it's just 1. Yeah, L1 is just 1. So the idea is that one picks pieces, one for himself and for all its children as well. Okay? So that's why it is Li plus 1. Yeah. Okay, so some supporting results here. So notice that the residue in each round of this or each execution of this while protocol, at each time the residue decreases by at least this fraction. Okay, and that's so it is easy to see why we get this. So 1 over n is residue according to the root agent. So according to root agent, every piece is of equal value. So that's why you have n in the denominator. The number of pieces allocated to non-trimmer agents is d plus 1. Right? The root agent is not the trimmer agent, and d is the size of the size of its neighbors. So d plus 1 is the set of pieces, number of pieces that are not allocated to trimmer agents. Trimmer agent size could be at most d. Right? So that's 1 minus this is basically the largest value the next round's residue can have. Right? Imagine in the worst case that all the trimmer agents trimmed in a way that your root agent finds all its value in the trimmed part. Right? So that can be at least 1 minus of this. Sorry, at most. Okay. So next round's residue can be at most this fraction of the current round's residue. So it decreases exponentially fast. As long as we maintain that the difference in the valuation between the allocations, partial allocations that we are maintaining is increasing, then there will be a point where this becomes arbitrarily small compared to the difference in the valuation. And we show that in order n log n number of in n log n executions of the while loop, this happens. Okay, and as soon as this happens, we remove the agent from the trimming set and put them into the equalizing set. So after this, the agents start equalizing. That particular agent start equalizing. We show that after order n log n runs of while loop, at least one agent gets dropped from the trimming set. Okay. All right. So right. So then we compute the query complexity in each. So there are n agents. So in order n square log n rounds, the while loop runs for order n square log n rounds, and in each run we have n cuts. So order n cuts. This first we need n minus 1 cuts that are made by the agents, the designated cutter, and then you have some more trimming and all that. That's just order n. So order n cuts. So the total complexity is order n cubed log n. I think it can be improved. This log n part can be removed, but it is polynomial time. Okay, and order n squared log n number of eval queries. Okay, I'll quickly go over the most general case where you don't have you have a general tree graph. So as it turns out, the line graph with n agents on a line is the hardest instance in this case, or at least this trick works in such a way that it finds the n agents on a line the hardest case. Okay, so to generalize this dominance that we have discussed for the depth-to tree, let's look at agent. So we'll first generalize this notion of dominance. Pick an agent J, pick an agent K. We call this K fair if all the agents with the larger index larger than J do not envy their neighbors. And we'll come up with a way to assign indices to the agents. But according to some index, we have indexed the agents first, and we call it K fair if the higher indexed agents do not envy their neighbors. Also, we'll come back to what storage is, but also there is some subset of pieces that they care more about what they receive than any of the pieces in this subset. Okay, this is called a storage set, which is very much similar to what we have seen for depth-to trees. In this case, the storage set would be the set of pieces that are picked by the neighboring agents, right? And then also, like, the third property is that it also depends on the graph. We don't have active childs in your depth-to trees, but all the agents having indices index J greater than K and have not yet picked a piece, those are called as the active childs. For those, we need to find we need to have larger valuation for J, right? This should happen for every J. Let's try to understand it slightly. So I will not go into the details. Let's look at the figure. So this is the figure. What we do is first index the agents in topological order. So the root gets the largest index. So there are 13 agents here. Now the storage set is this. So root cuts the cake into 13 pieces, or whatever residue is for a given round, that residue into 13 equal pieces according to the root agent. We traverse in the decreasing order of their index. So let's say that at some time you have 8 as K. Okay, the K value is 8. Now all the agents with the larger index 13 to 9 are the inactive agents, right? And active agents are the ones which are having the index larger. So those agents which are, I mean, these are dotted circles, they maintain only one piece, or only one bundle corresponding to themselves. Okay. Agent A13 maintains multiple bundles because it has active children. Okay. So the inactive agent might maintains his own bundle as well as his own piece, as well as the pieces for all its inactive children. Okay. And then, yeah, so inactive children, they don't hold any piece. What the idea is that we traverse the graph in this decreasing order and we remove NV one by one. Okay. This is done by a recursive protocol where it is not trivial, because agent A8 might give all the trimming to A9. A8 is not directly connected to A9. So A9 then gives it to A10 and then A11 and so on. They might not be they might not be neighbors of each other, but still they take part in trimming and equalizing in each row. Okay. Yeah. So we show that this protocol, I'll skip this, runs in order n to the power n to the power 2n. It has a query complexity of n to the power 2n. Still better, but still exponential. It's better than the Aziz and Mackenzie. The key takeaways are that, well, for a cyclic case, we improved this query complexity from tower of n's, tower of 6 n's to n to the power n. For special graph structures with the restriction on the depth, tree depth, we obtain. So this is the only known polynomial query complexity protocol for n agents in general. And again, you can talk about the star graphs, but that's a trivial case. Okay, this is a non-trivial, only known polynomial case for the non-trivial graphs. Right. And these protocols are easier to explain, easier to understand, because if we compare them with the Aziz and Mackenzie protocol, it's not a single cutter protocol. So this is a single cutter protocol which removes NV from one side of the graph to the other. In that sense, it is easier to understand and intuitive. Okay, so yeah, the immediate future work is look at locally NV-free allocations for cyclic graphs. What happens when there are cycles? It turns out that the cycles are also, I mean, the case for the cycles is also the bottleneck for the Aziz and Mackenzie's protocol. Right? So cycles are particularly hard to get NV-free allocations on. Can we improve the query complexity for these graphs, cyclic graphs? Maybe hopefully have polynomial query complexity. Can we write the query complexity in terms of some properties of graph itself? So for example, we looked at depth to tree, which had order n square n cube log n query complexity. What about depth 3? Can we characterize the query complexity in terms of some function of the graph itself, right? And again, can we get improved lower bounds for special graphs? That's okay. Well, thank you. Any question? Yeah. Yes. Yeah, so there are works which consider directed graphs. One of them is by Abebe and Kleinberg. Yeah. So undirected graphs are a little harder to yeah, but yeah, there are works which there's also Bayes work, right, on directed graphs. So there are other works on directed graphs. We just happen to, yeah, we consider undirected ones. Yes. Yeah. Oh, yes. So the answer lies in the 4 agents on line case, where we could easily get, so yeah, maybe just I'll go back to this picture. Yeah. So here, right, we always had one like we always had one piece which is trimmed and one piece which is added on, right? When there are more than 3 agents on one side, more than 2 agents on one side, it may happen that only one of these pieces is cut and there are 2 pieces that are added on. And when the immediate neighbor gets one of these 2 pieces, we cannot guarantee that the immediate neighbor gets one of these 2 pieces, does not get one of these 2 pieces. So this step here, right, and these 2, so this kind of interlocking is not possible with 3 or more agents. So this trick will not work. But in general, I think we can, of course, with order n to the power n, we can do this, but yeah, this simple trick won't work. It is only limited to the yeah. Yes. So agent gets dropped from trimming set if it is dominated by the root agent. Yes. Yeah. As soon as the root agent starts dominating a particular agent, that agent gets dropped from the trimming set. And this happens in order n log n rounds of while loop. Yeah. Yes. No, yeah. So can we improve this? That's the open question. Yeah. No, no. Right. At least I don't know one. Yeah, yeah. Yes. Okay. So this one. This one. Right. So we need something more than just VR of R. Okay. So uh, the 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 usual, I mean, even in the previous papers they've used this. Like as soon as the difference in the valuation exceeds that of your valuation for the residue, right? You do something. I mean, they define this as some event. Uh, However, we're not we're adding additional constraint on this. And the reason why do we have this is because this will yeah, so we optimize uh, over this n log n thing that we get. We optimize over how much we need, how smaller we need this part to be, so that we get like we get NV free allocation in least number of or least runs of the while loop. Okay, so it's coming from that. Yeah, yeah. So on one hand, you have that this term is decreasing exponentially fast. On the other hand, you have that the left term, that is the difference, is monotone increasing, except for the 0th k equal to 0. And we want to optimize over over the number of runs of while loop over which you get the domination condition. Right? Yeah, so that's how we define. So as soon as this happens, you just drop the agent from trimming set and yeah. Yes. Any more questions? Yeah.
What are like the disadvantages towards implementing a continuous algorithm for solving the fair division cake cutting problem instead of a discrete algorithm? For example,
Mm-hmm.
say you want to do a moving knife algorithm instead of following the query model.
Yes.
That particular case, like
Well,
that would lead to some sort of navigation.
yes, yes. So yeah, like algorithms like Austin cut, algorithms like moving knife and so on, they're difficult to implement in let's say by a machine, by algorithms itself. It is easier to so moving knife is sort of uh, I don't know. So as a computer program, that these are more easier to implement. How would you implement, let's say, moving knife algorithm in a computer program? Um, Also, like agents might, have like this is just a discrete version of this. Agents might prefer using this, may not have exact valuations for all the subsets or all the this works as a black box much better. They might be able to compare two pieces, or maybe able to tell you the cut and eval queries, give you more accurate answers for that, over a moving knife protocol, for instance, where agents might not have exact, like precise values for each uh, like tiny bit of piece. So yeah. Oh, but you still are in the Robertson web. But Austin cut, for instance, or maybe other procedures which are not Yes.
implement it efficiently. So, I mean, I can always simulate a moving knife. Any
Uh,
condition that this inequality holds,
right.
it's actually solvable. It won't, but the
But
question is why not use it after
but it okay, yes. So, but then you might not get the finite queries complexity. Yeah. So again, that gives answer to like, for example, any moving knife protocol you can simulate through Robertson web, not necessarily in finite time, but yeah. Yes. Approximations, yes. So we're not dealing with approximations in this work. There are a bunch of works which talk about approximate NV free allocations and so on. Yes. Yeah. And yeah, some of these can be achieved very easily in polynomial time and so on. Yeah.
Polytime algorithm in the number of curves we are using moving right? Are there any other specific classes of graphs for which you are having to get a very efficient algorithm for moving time, but you end up, but the comparative discrete answer is not
Right. I know. Yeah. So I know bunch of works by Bay et al. They use moving knife kind of Austin cut kind of idea, which still they're using, still they're not having exact NV free allocation. So still it is approximate. Yeah. So that's not again NV free, but that comes close to this setting in terms of the graph structure that they consider, right? But the yeah.
other graph structure for which
We don't know. So yeah, so this is an open question. Yeah. Directed cycle, yes. Okay. I don't know. It's a easy. Directed cycle is easy. So you just um, you pick an agent. Agent makes right. But yeah. Yeah, so this paper by Abebe and Kleinberg considers directed graphs, but they also talk about proportionality, I think, mostly proportionality, and they give, I think, order n squared protocol. Yeah, I mean, yeah, number of Robertson wave cut queries. Don't count, don't. Maybe, yeah, yes, sure. Yeah, okay. Thanks.
Yeah, okay. So now we'll break for lunch. Thanks, Ganesh, for the talk. Thanks. We'll meet at 2:30.
Yeah,
Yeah, it's too loud, I guess.
you were just bringing it close.
But I was asking, can we close it also? Is there option to close it? Because I. Yeah. Of course, just look at it. Does that? Yeah, I think.
I have my slides on.
You did something. Sorry.
So whatever I did, connected, sorry.
Yeah, I don't connect that.
Yeah, it did connect that as a, so if I plug this here, then it recognizes it as a keyboard.
Right,
Will it try that?
which is obviously correct. Yeah.
So shall we do that?
Yeah, but it won't work. Yeah, sure. Let's try.
Once for me.
I don't know. Yes, and then it says identifying a keyboard and now I don't know.
So there's something, it's an indication that it's working though. So what problem are you fixing?
You know how to get the clicker to work? You know how to get the clicker to work? It's working.
Yeah.
Oh, genius. Why did I ever talk to you? Okay. It's working.
Hands off. Sorry.
This pointer is also working. Pointer is also working. Yeah.
Yes, pointer is working.
How do you connect to your talk? Like just internet or?
Yeah, she's a good.
Hi. It's loaded on one of the browsers. I just need to run that on full screen.
And it switches easily.
You know what? You can just. Do you mind if she uses your laptop?
No, I don't know.
How about you just? Is it connected to the internet?
We just need to do Wi-Fi, whatever is working. Or otherwise LAN also, I don't know.
It's on a thumb drive, right?
Connected with your battery.
No, that thing is actually on a website.
Battery last कर जाए ना
58%.
That's like.
But connect, we can just put it there. I have full charging.
Hey, she's logged in somehow. I don't know how.
You do so?
I don't.
So.
I don't know, I don't have.
It's working.
Oh, fantastic. Okay, great. Good job.
ठीक है?
Actually,
Hi.
but there are my slides.
Oh, I see. Okay. Where are your slides? So this is an online thing, so I think I will have to drag it in this case. That's okay.
Yeah.
Sure.
Inspired to have such like fancy presentations one day. I'm heading in the wrong direction.
It
these
says
days.
Nildhara Mishra Pro. Did you see that? Pro with a star.
Boss.
I'm just saying.
I don't think there's overlap.
fact for solving the this you can just shout. I think that's
No, if you want, you can take it.
start now.
I can start.
Okay, so I welcome you all to the second session. I hope you all have like good lunch and a good break. So we'll start the session with Pallavi Jain, who's coming here from IT Jodhpur, and she'll talk about participatory budgeting.
Wang, Siddharth, and Sujit for inviting me. So I'll be speaking about participatory budgeting. So this is the first talk after lunch, and I hope I manage that you guys don't sleep. So what is participatory budgeting? Oh, I don't know. Okay. So it's a democratic process in which community members decide how to spend public fund. Okay. So for example, for a city, let's say we have 4-5 projects that we would like to fund for a city, right? For example, building a school, parks, bus stop, hospital, etc. Right? And of course, these cannot be built for free, right? Everything has some cost. And we also have some budget. Okay. So we of course need to choose what all we would like to fund, right? So of course, one thing could be just government decide, like that happens in our country, right? That just government decide what all projects should be funded, right? But another thing is that we can ask community members to either approve or rank or give numerical utilities over the projects, right? So here community members will play the role of voters. And our goal is to choose some projects that maximizes the voter satisfaction and the total cost is at most B, like within the budget. Okay. So this is basically, if you know about the multi-winner election problem or committee selection problem, you can imagine this as a weighted version of that problem, right? So instead of a committee of size K, now we are looking for a committee because now the candidates do have weights, right? So we are looking for a committee within our budget, right? So of course, whatever hardness are there, whatever rules we can think there, all those things we can think even here, right? But we need more things here because our objective is different here, right? Okay. Okay, so I said that this all is related to multi-winner election, but why am I talking about it in fair division workshop, right? So let's say that we have $20 million or rupees, whatever, and government wants to, government wants to think that how can we divide this fund to various projects, right? Now it seems familiar to fair division problem, which you looked at in first 3 talks, right? But here it's not just about that. Okay, again, as I said, that voters' opinion do matter. It's not just that government decide, right? And also it's not like the classical setting that every project need to be funded or we need to exhaust the budget. No, we don't have all those things. Okay. Okay, so citizens' opinion do matter here. So we can think of participatory budgeting as a fair division problem where the third party opinion also matter. And here the third party means basically community, voters. Okay. Okay. So one of the, now we need to think about the like fairness criteria here, right? How should we fund? Why this should be fair? So of course, one thing is that, basic thing is that we should think about maximizing the voter satisfaction, right? Because after all, we are doing all these things for the community, right? So we need to think about the voter satisfaction. So one algorithm which is used in Paris and Warsaw, that is the greedy algorithm. So they have the approval ballot there. That is, you need to just approve the set of projects you like, right? And then they compute the approval score, sort it, and approve the projects within the fund, within the budget, right? Basically, you look at the first project. If it is within the budget, approve it. Go to the second, and so on and so forth. Okay. But the one thing which is missing here is the interaction between the projects. What do we mean by that? Something happened. Okay. Okay, so color is actually not visible, but that's a blue region. This is the yellow region, and this is a green region. Okay, so colors are not that clearly visible. But let's imagine that these two areas are geographically close to each other. Okay, and then in this area, we are the project is to build the school, and in this area also project is to build the school. Okay, and in here the project is to improve the road between this green or whatever, this region to this region. Okay, so these are the three projects. We want to build 2 schools, and one project is to improve the road from one area to the other area. Okay. Okay. Now let us say here's a student who is basically living close to both these locations. Okay, so because of course he's a student, he would like to go to the school, right? So the good strategy for this student would be to approve both the projects, right? Because if he approves both the projects, then the chances that one of the school will be built is more, right? So he would like to, maximize the satisfaction and approve both the projects. Okay, but what happens? Let's say there are many voters like this green guy, right? Then what greedy approval method, which I just said, would do, it will approve both P1 and P2. But if you notice, these two projects are very close to each other, right? These two areas are very close to each other. So this is the extreme case of project substitution, because building a school at one of the location is good enough, right? But because we did not look at the project interactions, right? We just looked at if we just look at the voters approval, right? We would end up funding both these schools, right? Okay, so which we would like to avoid. Yeah, I'll come to that. Yeah. Right, it will depend on functions. Yeah. So another is like, let's say there's a guy who is living close to this this locate. Okay, so let's say he's living this close to this green area. Okay, so now this student can only go to the school if this road is there, right? So, and let's say there are a lot of students who are living close to this green area. Okay, and let's say they do approve both these projects, right? But the constraint now is that cost of P3 is high, right? Now, because the cost of P3 is high, right? P1 and P3 cannot be funded together, right? So, but greedy approval method, what it would do, it will approve P1 but not P3, right? So even if the school is there, it's of no use, right? Because the road is not there, students cannot go there, right? So this is the extreme case of complementarities, right? And you can also imagine that it's not just the school that is depending on the road. It could also happen that the school is in the remote location, right? Then even having this road is of no use. Like, where would you go, right? So both these projects are in complementarity, right? Okay. So in the classical PB, this is the input that you have projects, you have cost, there is a budget, and every voter approves something. Okay. Okay. Additionally, now here we have interaction structure. Okay. So I'll formally define how do we capture these interactions, but basically projects in a group, right, in a set, do have some interaction. Okay, we'll quantify these things later. Okay, so now here the goal is to find a bundle within budget, right, that respects voter preferences and also consider interaction structure, right? Now, when we are talking about respect voter preferences, we need to talk about the aggregation methods. Okay. So we can so this is the paper with Nimrod and Christoph, and this was in HY 2020. So we considered utilitarian method. Okay. But of course, we can consider other aggregation methods as well. Okay. Like, for example, egalitarian, you heard about Nash social welfare. We can study all those things here. Okay. So in utilitarian, voters do get certain utility, and goal is to maximize the total utility. But here's the catch. Here, the utility does not only depend on the approval set, but it also depends on the interaction structure. Okay. Here we define it using a function. Okay. So this function is from set of integers to the set of rationals. Now, Fi is the utility that a voter we get from a part in the interaction structure. So this Z and that Z is different. This is a set of partition of the projects, and that Z is the integers, right? So you get from a look at a part, right? Look at the projects funded that are approved by a voter in this part, right? That is the utility you are getting from this part. Okay. So mathematically, so this is the utility of V is the voter here, and B is the bundle that we choose, right? So this is we go over all the parts. Okay. And this is the how we compute. So basically, you are computing satisfaction for every part, right? And then you just take the summation. Now here also, instead of summation, here also you can think about egalitarian setting. Okay. So you can do all those combinations here. Now utility or total utility from a subset is we just take the summation over the voters. So is there any question in the definitions?
Reduce to standard without the structure.
Sorry, say it again.
If each capital Z was a singleton, this would reduce.
Correct, exactly. Right. This is a normal setting then, without interaction. Right. Which is like polytime solver problem, yes.
Now it's like, and you're not assuming any concavity or convexity.
I will. Yes. So capital Z is basically the partition of the projects, right? It captures that what all projects in the same group, right, basically have the some interaction between them. Okay. So for example, I discussed about substitution and complementarities, right? But these are not the only possible interactions. It could be anything. Okay. Right. B is the voter here, yes. So, okay. So, okay, I should say this. So by V, I mean, I also use for approval set. Therefore, that also I'm using V. Okay. I'm using V for voter as well as for the set approved by voter V. No, it just depends on count. Yes. It does. It depends on what is my function F. For example, convex function would capture that thing. Yeah. Yes. So here we are considering that it's partition, but in general, one may consider.
For example, it's concave,
Substitution. Yes.
Considers the interaction of that similar products and that.
Right. So it depends on what do we mean by similar, right? For example, in the complementarity, there is no similarity between the projects, right? It's just they do depend on each other. For example, that was one example, that road and school, right? There could be other examples. For example, hospital and pharmacy, hospital bus stop. Correct. Okay. Maybe battery is down.
Yeah.
Battery is down, I think. I mean, it's just taking some time. Yes. I can't hear you. Okay, so this is this Z is basically the partition of projects. Z belongs to Z, meaning Z is one set, right? So one set now you have. V is we are using V for voter as well as for the set of projects approved by voter V. Okay, so all these are sets now, right? And B is the subset of projects that we choose, right? So all these are subsets now, right? And then look at the intersection, right? So it basically captures that, look at the approval. So you need to pass it like this, okay? This is the approval set of V in set Z, right? That is funded. Okay. This B, okay. Did I misuse the notation? This B is basically, this is not the budget, it's the subset of projects. No, that is a subset solution that we choose, right? That is funded. Exactly. So it is like a generalized version of committee selection problem. Okay. Capital B set of voters. Capital B, yes. B is subset of P, subset of projects. That can be funded. That is funded. Okay. So think of it like this. You have a subset of projects, right? Corresponding to that, you compute the utility of every voter. Okay. Now you compute the utility due to this subset of projects, right? And what would be our goal? Our goal would be to find a subset of projects that maximizes this value. Okay, within budget. Say it again. That's right. F could be any function. So this is how we define, right? Because for example, substitution, right? So if you consider linear function, right, then F2 is equal to 2. It means that if you are funding from the same group, right, if you have taken two projects, right, that are approved by this voter, that are funded, etc., etc., then your utility is 2. If it's a linear function, right? If it's a right, but it could be something else also. Why it needs to be linear, right? For example, I can very well say that, oh, I don't care how much you fund, you will get the same utility. I don't care whether you fund one project, but you fund two projects, 5 projects from this group approved. I don't care. Utility is going to be same. That's constant function. We are not considering this. So these are like, there's no valuation like project wise. As a voter, I can approve something more or less. Okay. So I didn't like projects do have cost, but there's no value associated with project. Identical value is not associated with that. As a voter, I can rank something, you know, more or less. V is okay. So everybody needs to understand this, that V is a voter as well as the set of projects approved by voter V. Okay. So this is the convention that is used in a multi-winner election, that V is a voter as well as a set of projects approved by voter V is also denoted by V. So see, all these things depend on what is our function, okay? These definitions do not depend on whether we are talking about substitution, complementarity, or something else, okay? So that is motivation. Now we are defining the problem, which could be very, very general. We are defining a general problem now, okay? This has nothing to do with it will depend on your if you have substitution, then what kind of function you should define. This is what you need to think. If it is complementarity, what kind of function you need to define. This is what you need to think. Okay. Or if you have some function, does it really capture something in real life? This is what we need to think. Okay. Okay. So you imagine that it's just a partition of 4 projects. Okay. It's a partition for now. It's partition given to you. Okay. 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 So we are assuming some properties of these functions. Okay. Which we think that makes sense for this application. Okay. So the one thing is that non-zero function, right? You should get some utility if your approved projects are funded. You should get something, right? Okay. Fi is greater than or equal to 0. So here we are assuming that you're not getting negative satisfaction. Okay. So, but here you could consider that. Okay. Here we are not saying that there's no chaos. Okay. So the utilities are positive. You are getting positive satisfaction. It's not negative. Okay. If you do not fund something, it's 0. Sorry, if you do not approve something which is funded, it's 0. Okay. It's non-decreasing also. Okay. So here when we thought about this problem, we thought that, okay, why the utility should, satisfaction should decrease, right? If suppose it's a substitution structure, let's say, okay, and let's say that something of my choice, one project of my choice is funded, right? If two projects are funded of my choice from the same part, then my utility should not decrease. It may remain same, right? But why will it decrease? Okay, so we are actually discussing, and Christoph, who is one of the author, he suggested that. So he's a non-vegetarian guy, and he was eating lunch with me. So he said that that we can actually have this because he might like to eat vegetarian food 1 day, 2 day, 3 day, right? But if it goes over a month, he would not like, right? So it is like, so it may happen that sometimes it is decreasing. Okay. So the moral of the story is that it may happen that there might be scenarios, there might be applications where we need to consider non-decreasing, sorry, decreasing functions as well. But here we do consider non-decreasing. Okay. So concave functions do capture substitution effect, and convex capture complementarity effect. Okay. Okay. So going to the classical complexity. So the problem is NP hard. So you see that is the range that we know the result, right? Even for the constant number of approvals. And it is also W hard with respect to budget. Like the reduction is same, it's due to the independence set as far as I remember. So W hard meaning that we cannot hope for an algorithm that runs in GB with polynomially dependence on the input size, right? Here GB is arbitrary computable function. It could be exponential. In fact, in general setting, it is exponential. Otherwise, you will end up solving problem in polynomial time. Okay. So this is a running time, right? So we are saying that we cannot hope for an algorithm that has such a running time. Yes, it should be just computable function. Okay. So morning talks were mainly about classical complexity or approximation algorithms. Here we have some parameterized results. So with respect to budget, we already saw that, like I already said, that it's W hard. We also consider the maximum number of approvals by a voter, right? So because it is NP hard, even for the constant number of approvals, we cannot hope for an FPT algorithm with respect to this parameter. Maximum size of a part S in interaction structure. Okay, maximum size of a set in your partition. Okay, in case interaction structure is confusing, just think of it as a partition. Okay, so this is FPT for integer valued functions. Yeah, so this is also one parameter M minus Z. So we can imagine that if the sets are of small size, then it is captured by our third row, result in the third row. But if the sets are like size of the set is large, then actually this M minus Z is going to be small. Okay. Okay. So with respect to number of voters also, we have okay, I'll define all these things. So I'll discuss quickly these two algorithms. Okay. So the first algorithm, actually, I just need to give a overview of the second result. Okay. Okay. So let's say this is an instance of max FPB, and let's say Z is the, we have Q sets. Okay. So if we have Q sets, then maximum possible approval score is this, because from a set, we are going to take at most S many projects, right? So the valuation that your approval score that you are going to get is F of S, right? Over the sets, right? You have Q sets, Q into Fs, and then you sum up over the voters. So NQFS. Okay. So we can just solve it using simple dynamic programming algorithm. Okay. So Tij basically, I captures here the first I parts of Z. We are going in the sequence, and J is the utility. Okay. Okay. So just using this simple dynamic programming, I'll not discuss this because you all understand dynamic programming. Okay. So using this, we can compute it, but you can notice that the running time is coming due to 2-3 factors. You have minimum of, okay, so I think this works. This, right? So you're trying the subsets of Zi, right? So this is one place, and this is another place that we will get the this function of S in the running time. Okay. Exactly. This is like knapsack. Yeah. But when the function becomes eventually constant, which means that there is a point I after which the function is constant. Okay. In this case, we can actually pre-process the data. Okay. So if there are more than I projects in a part of Z, right, such that they are approved by the same set of voters, then we can get rid of the expensive project. Okay. So it means that in a part, I can look at the subset of voters, right? And corresponding to that, we can bound the number of projects, right? So we have 2 to the power n subset of voters, right? So this is how we can, in a set, we can bound the number of projects, right, by 2 to the power n. Okay. So of course, we should have I also here, right? Because for a subset of voters, we have I projects in a set, right? But here we are using the convention that F is in the problem definition. So F is fixed. It does not depend on input. So I is also fixed, where it becomes constant. Okay. Okay. So, okay. So here I need to say this, that if you use the previous algorithm, right, now we can say that that algorithm itself runs in FPT with respect to n. Okay. Because now the number of, the size of the set is bounded by some function of n. Okay. So everything is bounded by this thing. Okay. 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 So with respect to n also, we can use the similar things for integer valued functions. Okay. So here I will use the ILP, mixed integer linear programming. So for a set, the cost of, so okay, before going to the formal things, basically for a set, we will use mixed integer linear programming to compute the bundle that is going to be funded. I cannot compute across the project sets, but within a set, I will compute using integer linear programming, mixed integer linear programming. Okay. Okay. So for a set Z in my partition, the cost of a cheapest bundle with total utility at least U can be found if exist using mixed integer linear programming in this much time. Okay. So we have roughly 2 to the power n variables. That is why using Lenstra we are getting this. So there is a paper by Robert Brederick et al. That talks about that that consider the concave and convex functions, right? So using that we have this, because I'll not go to this because this is a bit long. But cost you can capture using the concave functions, and utilities you can capture using convex functions. Okay, and that is how you can compute it. Now we will go back to our previous dynamic programming algorithm. Okay, so you can, so one entry, because it is same, right? Because for the first set we want to find a cheapest bundle that achieves the utility J, right? So I can just find it using mixed integer linear programming, right? Now instead of using this step where we are going over all subsets of Zi, right? what we can do, yeah, so I can use this MILP, right? So here I is to capture the first I parts, right? And J is for utility, right? So minimum of U, here I am guessing what is the utility for the last part, jth part that I'm talking about, right? Once I know that, I can compute the bundle for the jth part using my mixed integer linear programming. On for the remaining first j minus 1 parts, I've already stored in my DP. Okay. Thanks. Okay. So I don't want to go to previous slide, but I'll say some open questions there. So if you notice, the algorithm was 2 to the power 2 to the power n. Okay. So one question is that to improve, can we hope for single exponential time algorithm? Okay. Another thing is that eventually constant function depends on function of function, right? It had f of s. Now because s is function of s is function of n, f is also, right? But it could be towers of exponential, right? So can we improve that? Okay. So these are the two questions. Another thing is that we only have algorithm for integer valued function in general, not for constant. For constant, it's fine. It could be anything. Okay. But because we are using actually DP, right? So the same idea that we use for knapsack, right? So that is why we need integer valued functions. But we don't know what is the complexity with, forget about real. What is the complexity with respect to the rational numbers? We don't know that. Okay. Okay. How much time I have? I think 15 minutes, right? Okay. 30 minutes. Okay. 1-3. Okay, sorry. So I'll quickly discuss one more fairness criteria. All organizers can relate to this fairness criteria actually. So all the money cannot be spent to one type of projects. Let's say we are organizing an event. I recently organized a winter school at IIT Jodhpur, and we actually did this thing, right? We had total budget and we had very, budget was not much. Okay. So we had to classify that, okay, how much we can spend for travels of speakers, how much for accommodation, and so on and so forth, right? And we have to do it, right? Right. And because of this, I could only invite 2 external speakers. Okay. So, yeah. So I hope you all agree that in participatory budgeting, right, we also need to think about it, right? Okay. So along with this classical instance of participatory budgeting, now you also have a group of projects. Okay. A family of group of projects. Here it need not be partition. Okay. It's a subset of projects. Okay. And the goal is to find a bundle, which is, okay, bundle means a subset of projects. Okay. So we have to find a bundle that maximizes voter satisfaction within global budget, as well as we need to respect the individual budgets, okay, for each group. Okay.
If satisfied, is there like a number that's given?
So satisfaction, I'm not saying group wise. Group wise is only budget. Satisfaction is total. But indeed, that is also one of the question.
This is grant budget as well as
Local budgets, group wise budgets. Yeah. So formally, the question is this: we have a set of projects with their cost functions, a set of voters with their approval ballots. Okay, a family of groups of projects with their budget function, right? And here we are just considering the natural numbers because it's like cost, right? So we can. But of course, if you want to generalize, you can think about general values. So, and a global budget limit and a desired utility U. Okay. And now the question is there a set of projects such that the satisfaction, again, I'm taking approval score, right? So we are saying that how many projects are funded from the approval set that count right? That count is the satisfaction of a voter, right? And then you take the summation of the voters, summation of the satisfaction of voters, right? That should be at least U. Total cost should be at most B. And for every set, look at the subset, look at the set of projects in F that are funded, that cost should be within budget. Okay. So this problem is complexity wise quite interactable. I should not use the word hard here. So Bmax is the maximum budget over the groups, right? S is again the same maximum size of a set in your family, and F is the approval set, maximum size of approval set. Okay. Yeah. Okay. So it is para NP had been for these parameters, like when all plus meaning when all these things are constant, then also the problem is para NP hard. Okay. Okay. So with respect to this problem is W1 hard, again independent set, but here U is not constant. Here U will be the function of K. Okay. Okay. So with respect to G, the number of groups, we have XP algorithm, but FPT is still open. Okay. Then we try some combined parameters and it turned out to be FPT. And then we have 1 plus epsilon FPT approximation with respect to the number of groups. Okay. So FPT approximation, for now we can just imagine that it is a 1 plus epsilon approximation algorithm that runs in FPT time. Okay. And parameter here is G. Okay. So Siddharth said that if we have utilities, group wise utility also, that this much you want to achieve, this much utility you want to achieve from every group, right? That problem is W hard with respect to G using arc supply problem. Okay. But without that constraint, we don't know. Okay. Okay. So I'll quickly discuss this algorithm. I think I can manage in 10 minutes. Okay. Okay. I think I need to point there. Okay. So quickly, so the idea is that we have an instance of group PB, and then in FPT time, we will reduce it to again an instance of group PB problem with an additional constraint. Okay. The constraint is that a feasible solution has to contain exactly one project from each project type. Okay. So what is the project type? The family of groups to which the project belongs. That defines the type of a project. Okay. More formally, a project is of type R, where R is a subset of our family of group of projects, if it belongs to all the groups in R and to none of the groups outside R. Okay. So this is the phase 1 of our algorithm, that we do this reduction. After that, we round down approval score to the closest multiple of 1 plus epsilon, and then we apply branching algorithm. Okay. So let us quickly look at this reduction part. Let X star be an optimal solution. We cannot compute it. It's like just hypothetically assume it. Okay. So for every project type, just guess what is whether X star contain at least one project of that type. Okay. If it does not contain, delete all the projects of that type. Okay. Now, whatever I have, I know that from each type, at least one of the project is in X star, is in my optimal solution. Okay. By the way, so the problem that I said, that was the decision version of the problem, right? Here I'm talking about approximation, max group PB. So here we are trying to maximize the utility. Okay. So we are trying to approximate utility. Okay. Okay. So because the project types is 2 to the power G, right? Because project type is basically defined on the basis of the subset of groups. Okay. So time taken for this guessing is 2 to the power G. Okay. Now for every project type, A is the maximum possible approval score, and then that we can compute, and it is polynomial. Okay. So we compute cost of RV, which is minimum cost of a subset of projects of type R, whose total value is exactly V. Okay. So this, you believe me, this can be just computed using dynamic programming. Okay. Okay. Not only, okay, if such a, it may also happen that such a subset does not exist, then we just store infinity. Okay. We also keep, like, store a subset that realizes this value. Okay. So the use of this bundle RV will be to get back the solution of the original problem. Okay. Okay. Now we create a new instance of group PB. So for every project type and every value such that cost is not infinity, we add a project of this much cost. Okay. So for example, basically for project RV is like a indicator that you have of type R, we can achieve utility V. Okay. There is a bundle that does this thing. Okay. We may not take it, but it is there, right? So basically now you can think that for a bundle that could be potentially part of my solution, right? I have a project for this. So this bundle I have grouped to one single project. Okay. Okay. So type of all the projects is of course R, right? Global budget remains same. And for every set in my group family, we add a group, because we are still constructing an instance of group PB, right? So we need to also construct this family of groups, right? Okay. So we add a group TF that contains all the projects such that R contains the group F. Because recall that R is subset of your family and F is one particular set. Okay. So this is the definition. TF is project RV. Okay. So again, this is one single project. Okay. Project RV such that F belongs to R. Okay. Now budget of group TF is same as F, right? Because you cannot fund more. You cannot fund more than that from this particular F. Okay. Okay. So let's say I was your original instance and this I prime is the new instance of group PB. Okay. So now how did we, like, we first guessed if you are going to have a solution of one particular type, right? And then you grouped it accordingly, right? A group contains projects of the same type, right? So I know that from that particular type, I need to fund something, correct? So that is why now we have reduced the problem where from each type, we need to pick one project, exactly one project, right? Okay. So, and we can show that every feasible solution to I prime can be transformed to feasible solution of I, right? Because here a project corresponds to the bundle in the original instance I, right? Okay. So this was our phase 1, where we reduced our problem of group PB with an additional constraint. Okay. Now let's go to phase 2. So we just round down the approval score to the closest multiple of 1 plus epsilon, right? Now let's say this is our new instance. We can show that the loss in the utility is only going to be 1 plus epsilon. Okay. So now when we round down, right, then it is possible that two projects are of the same type with different approval, but they are rounded to the same value, right? Just keep the one with minimum cost, right? Okay. So after doing all this bucketing, after doing all this rounding, right, we know that we have only log of a many values, right? Now what we can do of each type, right? I also know that from each type, I have to pick something, right? Yes. Yes. Okay. So now we know that because from each type, you have to fund something and these values are not too many. What I can do, I can branch, right? Branching means that let's say you have 5 projects of the same value, right? Same type, right? Then we can say, oh, are you going to fund this one? Are you going to fund this one? Are you going to fund this one? That's all. Okay. So basically, you can also think of it as like you are guessing which project you will fund. Okay, it's the same terminology. Okay, so we do branching, and then because you, for every type, these are the possible options, right? And that's all. T is the number of types. Okay, and number of types we already bounded by 2 to the power g. Like by definition, it is bounded by 2 to the power g. Okay, and this we can solve using the Cauchy-Schwarz inequality, I think. So this is like classical result in parameterized complexity. You can do this. Yeah, I think I'm within time. Okay, so here we have some of the open questions. So main open question here is the parameterized complexity with respect to G. Okay. FPT approximation in 2 to the power order G time. Again, here also we have double exponential time algorithm. Of course, we can try different aggregate, like other things are, natural future directions. Try different aggregation methods, try cardinality constraints, try to consider more other project interactions, because some of the results are for arbitrary f, but some of the results depends on whether f is concave, convex, and so on and so forth. Okay. Thank you. Any questions?
So there are disapprovals. Can we capture that pose in F, or is there any other work?
So this okay, so there's actually no follow-up work here, but disapproval, basically what is not funded is disapproval, right?
Say road construction. I feel it will be disturbance to me because it's going by my house, and that should not be constructed. So I disapprove that.
So here, whatever, so approval is basically the subset of projects, right? So whatever you do not approve is disapproved. Here we do not have -1s, so it's a 0-1 setting, right? It's binary. Things will.
Is there any follow-up work?
No. But actually, that's a good thing, because this is the setting where we talk about the chaos, right? Because we do have negative things, right? Then we need to worry, and the things drastically change when negative numbers comes into the picture. Yeah. I can give you a charger if you need.
Battery is fine. You just need to point it in this direction or something.
Yeah, there's 50% battery. So actually, yeah, it's behaving like that. If you remove it, then it will behave better. Okay, much better than us.
Very nice talk. Next up, we have Neeldhara Mishra from IIT Gandhinagar, and she'll talk about equal shares and then something more.
Let's hope. I don't know if we'll get there, but okay. Thanks so much, Nidhi. And thanks to the organizers for having me. Oh, okay. All right. This better? I'll stand there. Okay. Am I audible at the back? Yeah, awesome. Am I audible to you? Okay, very good. They may not be monotonic. So anyway, all right. So I'm going to follow up on Pallavi's theme of participatory budgeting. And I'm going to talk about a method for doing participatory budgeting called equal shares, but it's going to be in the rudimentary vanilla PB setting. So we're not going to have all the fancy interactions and the group budgets and so on and so forth. That's just material for my last slide on future directions. So that's going to be worth considering, hopefully. So let's see. I don't know if this works. Okay, maybe not. Yeah. Okay. Good point. All right. Oops. So I don't know which cursor this is, but okay, doesn't seem to be reacting to anything. Take it. I will live with that. Oh, I see. Oh, thank you. All right, good to know. Okay, this seems to have a spring action, but we can live with that there. Thanks. Okay, all right. So So I swear I made these slides before Pallavi's talk, but I'm going to borrow her example of conference organizers who want to, I think she had a nice pie chart where she said accommodation and speaker expenses and blah, blah, and registration kit was like some 10% of the budget. So unfortunately, registration kits don't get a big chunk of the organizer's budget. So let's say we have 1,000 rupees to build a registration kit per person. And let's say we have, okay, I'm going to continue to struggle with this thing. Sorry. Whoops. I have no idea how we jumped ahead so far, but all right, maybe I'll just do. Yes, indeed. I know. All right. Hopefully, no, excuse me. I think this will persist now. Okay. All right. Let's hope that doesn't need to be recognized as a keyboard all over again. I don't mind killing time though. Let's see. I'm happy to use the physical keyboard. It's fine. Oh, maybe I have to click back. Okay, good. Maybe I should just not venture out of the Bluetooth radius of this thing. All right, so as it turns out, we have things that can go into the registration kit. So I'm just zooming in into this example. And our stakeholders are going to be the volunteers who are helping out with the conference. They should have a say in terms of what goes into the kit. And they're going to have different opinions about what should be there. And notice that these numbers here are just what these items cost to put in the kit. And let's say our volunteers here have these opinions, which is basically to say read it column-wise. So this lady here likes the bottle, doesn't care for the notebook or the puzzle, wants the bag, the folder, and the pen, okay, and so on. And what would be like a natural way to decide what goes into the kit is to say, well, let's look at the popular options, right? And keep picking the most popular options until we run out of budget, right? That makes sense? Yeah, it's a natural greedy thing to do. And in this case, if we pick the most popular options, I think the most popular one is the bag with 7 votes. And the next popular one is the bottle with 6 votes. So we've already exhausted our budget with this. Remember, we had like $1,000 to build our kit. And so that's all the kit is going to be if we do the most popular vote. And what's the problem with this? Yeah, the 3 poor boys are totally unhappy, right? Because they didn't get anything that they liked in the kit. And this is somehow not so nice for them. So, okay, so this is, so we're going to come back and try to fix this example in a bit, but I'll just build on again something that Pallavi said about how participatory budgeting is very closely related to multi-winner voting. So in multi-winner voting, we normally have a set of candidates and voters express preferences over the candidates in some way. So for example, in the previous instance, we had the so-called approval voting, I call it Tinder voting, swipe left or swipe right on each of those candidates, right? So, so that's the simplest kind of preference that you can think of. But there are more sophisticated things you can do, like ranked votes and so on, but that won't be relevant for now. So I won't go into it. Now, in multi-winner voting, in normal voting, you try to find one winner. In multi-winner voting, you try to find many winners. So typically, you have some sort of a threshold K, and you're trying to find K winners. Sometimes it's also called committee selection for reasonable reasons, I think. And of course, this is a fuzzy bit. We want to make all voters happy, and there could be different ways that you could try and formalize that. We hope we make everybody happy, but how is this related to participatory budgeting? We're in a natural way. So for us, our candidates are projects, right? And our stakeholders are voters, and then they express preferences as they just did. And K projects are chosen. That's not quite what we had, because these projects, the main difference really is that projects come with costs, right? And instead of choosing K projects, you managed to fit it in within a budget of K, which is why this reminds you of knapsack as it did. So if you do have a situation where all projects have unit costs, then this mapping is quite exact. But if you're going beyond the unit cost setting, then that's like a knapsacky multi-winner voting situation is what you have. So this is just a recap. But let's talk about how do we make stakeholders happy. So one way to talk about this is to kind of talk about properties that you want your mechanism to have. So here's a very natural thing that comes up in at least the voting world. And it's called justified representation. So suppose you're trying to pick K winners and you have N voters. So if you're N over K voters, you feel like you should have stake on at least one seat among those K winners, right? So if you're trying to select a committee of 10 people and there are 100 of us in the room, and if there are 10 of us who have a common preference, so the weight of 10 people within a room of 100 is like, that's a ratio of 1 over 10. And so you're trying to select 10 people. So you feel like you should have a stake on one slot, one of those 10 slots, right? So that's, in some sense, the theme of proportional representation. So, so if you have N over K voters who all like a common candidate, at least one common candidate, then you would want to make sure that in your final selection of K winners, at least one of these common candidates is in there, right? So that's reasonable. Or well, maybe, sorry, a better way to say it is that all of these voters have at least somebody that they like in the outcome. So it doesn't have to necessarily be the common candidate, although that would be probably typically the most efficient way of doing it, but it doesn't necessarily have to be.
Every subset of N by K voters,
right,
whose approval intersect,
correct.
They have
The final committee has to satisfy all of these voters. Yeah, with at least one slot. Yeah, exactly.
So this difference of saying all candidates were more than N by K voters. That's a difference.
That's like more like the, I guess, the Monroe style of representation that you're talking about. Like you're talking about support from the candidate's perspective, right? Right. That's yeah. This is from a voter kahak wala perspective. Correct.
And they go away and select themselves, then
yeah. The core notion comes into play, Mummy. Oh, it just sleeps. Oh dear, I see. Okay. Okay. I think I might need your help to unlock this. Sorry. Sorry, there was a question on the back. Mm-hmm. Correct. You're right. That's okay. So basically, all that we are saying is that all of these fellows here have to have representation. It doesn't have to be via the common candidates. So all we are saying is that all of these voters see at least one person in the final committee that they like. All N by K of them? Yeah. Yeah. Mm-hmm.
Summary the union of approval, not the intersection. That is represented for justified. Probably extended justified.
Correct. So I am talking about the union. So all I'm saying is they have at least one representative per voter. So I don't mean that that representative is from the intersection.
From the union.
It's from the union. Yeah, that's what I mean. So these voters, each of these voters should have at least one representative. And that's basically saying that each of these voters see somebody they like. So it's the union. Yeah. Maybe I should just, sorry. Okay. So AI is the approval set of the ith voter, and then each of these voters see somebody in W. Yeah, so they're happy individually. If I was picking a committee, I might find it easy to just pick the common guy to satisfy everyone in one shot, but that may not be, with other considerations in place, that may not be a valid way to do this. So yeah, sorry if that was confusing, but that's justified representation. Yeah, sorry for all the English, but then you could extend justified representation or generalize it in this natural way where you give some sort of a weight, saying that if you have, if you feel like you deserve representation over L seats, then you should get representation over L seats. And again, it's from each individual voter in this group of L times N over K voters independently sees L people that they like. This is extended justified representation, and both of these notions are fairly standard as far as multi-winner voting is concerned. And one of the things that these folks do, by the way, I don't remember if I mentioned this because I think my pointer was acting up in the start. So let me just say this for the record. Everything that I say is based on this paper here, Proportional Participatory Budgeting with Additive Utilities, which appeared, I think, in NeurIPS 21 or something like this. And they have some exciting updates on the preprint version on archive. And they have a lovely website with basically a lot more information. So all of this is stolen from a bunch of places. I have proper references at the end. So, so one of the things that they focus on is translating these axioms, which are very familiar in the multi-winner voting scenario, to the participatory budgeting scenario. And that's what we'll talk about as we go along. But before that, let me also, yeah. This is a weaker notion than the core. That's right. And the core is mysterious, as you know. So one of the things they do is actually come up with also a different notion that they call fully justified representation that sits between the core and EJR. So it's a strengthening of this, but it's not as strong as the core. And they do come up with a rule that satisfies FJR. So that's kind of interesting. Okay, so here's proportional approval voting, which is a classic rule in a very serious sense. It goes back to the late 1800s or so, but I think it's been formally looked at only relatively recently. Yes, sorry. Sorry. On the previous slide here. Yes, so, okay, so you L here, right? Yeah, so I suppose you satisfy EJR up to, yeah, I mean, you satisfy EJR fully if you satisfy it for all L. And JR was just L equals 1. And I suppose if you satisfy it up to, so values of L make sense between 1 and K inclusive. So you could say you satisfy something between JR and EJR if you satisfy it for a few values of L. But integral in this setting, yeah. Right. So this is all integral choices between 1 and K makes sense. Yeah, okay, cool. All right. The next slide, yeah, this is right. So I suppose you could say that this is harmonics. Yeah, basically, exactly. So here, okay, let's say you have a committee, you have an election. I mean, you're proposing a committee. I want to talk about how nice is this committee from a voter point of view. So as a voter, well, I'm going to look at how many folks that I like are on the committee. And the number of points I give this committee might just be the number of people that I like, but that's sort of a course thing to do. It's okay if you're in kindergarten to propose that definition, but as you grow up, maybe you start talking about diminishing returns and fancy things like that. You could actually plug in other functions here, but I'm going to say, you could plug in other forms of capturing diminishing returns. But for the first chap that I see on the committee that I like, I give the committee 1 point. For the next chap I see, I'm less excited, so I give half a point and so on and so forth, right? So these are the points that I accumulate as I see more and more people that I like on the committee. That's the PAV score that I give to the committee. The total PAV brownie points that a committee gets is the sum of the PAV scores of all the voters for this committee. So hopefully this definition makes sense. And this is a pretty cool voting rule in the sense that it satisfies EJR. It satisfies EJR in a somewhat strong sense. For a suitably defined class of voting rules, you could actually say that PAV is the only voting rule that satisfies EJR. So that's pretty, it's almost a thing that characterizes EJR. So that's pretty cool. Less cool is the fact that it's a hard rule to compute. You can reduce from, I think, something like independent sets. So it's hard even when all voters only approve 2 candidates. So this is a bit sad. Also, once you start playing around with EJR and try to take it to the PB setting, which we haven't formally defined yet, so this is a bit of spoiler alert, where we're saying that if you try to extend PAV-ish rules to the PB setting, then it fades pretty dramatically. So we're going to come back to that later as well. So let me come back to a little example where we are hopefully convinced that the greedy popular voting idea was sort of miserable for at least a few voters, and we want to spread the cheer and be more sort of uniform in how we make people happy. So let me talk about the method of equal shares, which promises to do this to at least a fair extent, as we will see. So I'm going to spend some time just talking about how the algorithm works, and if nothing else, I think if I can at least be clear about the mechanism, I think that's at least one takeaway from the time that you're spending here, right? So,
The existence here is applied only to that. There's no other. PAV is hard.
Right.
It does not show like you could have
Correct.
some other policy.
Correct. But yeah, right. I think there's also a separate argument for the existence of EGR allocations. I don't think the outcome of PAV is the only way that we know this, if that was your question. But yeah, I think there's an independent. In fact, this is also true in the PB setting, that there are proofs. So in fact, even though PAV does not work for EJR, and in fact, there's a result which says that no efficient mechanism can satisfy EJR. And that's indirectly why the method of equal shares does not satisfy EJRs, because it's a strongly polynomial mechanism. However, there is an existential argument for saying that EJR is doable, is achievable. No, it cannot be achieved in polytime, but it exists in principle. So yeah, so those are two separate findings.
So for participate, but take there is hard.
Right.
Multi-winner.
So for multi-winner, I have to sanity check if there is a polynomial time method that produces an EJR outcome.
Local search.
The local search. Okay. All right. Yeah. So there you go. Cool. Yeah. And yeah. Okay. So fair enough. So in the PB setting, it's hard, but in the multi-winner approval setting. Okay. Perfect. So thank you. All right. So okay. So coming back to this, I'm going to define. I'm going to try and describe how the mechanism of equal shares works and why it's better than the stupid greedy thing that we were doing earlier. Okay. So the first thing that we do is we take all the budget that we have and we divide it equally among everybody who is voting, all the stakeholders. So here, let's say we had $1,000. We are going to take all our 10 volunteers and give them $100 each. Okay, so that gets divided. And then, well, we bring in the things that we are voting over. So recall that these were the things that we were trying to put in the kit. And what we are going to do is find the project that has the highest number of votes, find the thing that is the most popular for now to begin with. And then what we are going to do is catch hold of all of these people who said they like this and make them pay for it. Okay, so the bag costs $700. There's 7 people voting for it. And then what we are going to do is ask everyone to pay up. So these fellows didn't care, so we leave them out of the picture, but everybody else puts $100 in the hat and buys the bag for the kit. Okay, so the bag is in, but these volunteers are now out. This is the key thing for equal shares. We don't count voters who have no money left. Because the intuition is that, well, if you've run out of money, that's probably because you've already had your say. You've been pretty loud in the room. Now get out of here and let the other people actually have their say. Okay, so that's kind of the intuition for what we're doing. So these fellows now are out, and now we recount the votes based on the people who remain. So notice that the water bottle is now out of the picture. It has 0 votes, and then we have 3-3. The bag is in already, and then 1-2. So those are the new recounted votes based on who has voting power now, right? So okay, so what are the most popular options? There's the puzzle and there's the book. And ordinarily, I would talk about a tie-breaking mechanism here, but we don't need to break this tie simply because we cannot afford the puzzle anymore. We've already paid $700 for the bag, and our total budget was 1,000, so we only have 300 that remains. So the puzzle is out of bounds. We're going to work with the notebook, and the way we're going to work with the notebook is have these 3 kids here pay for it. So it's 270. Divided by 3 should be something easy because that's how I picked the numbers. 90. Okay, yeah. So they all pay 90, and they're left with 10 rupees each. And the book is now in. This is what we're left with. So the votes don't change now because people still have, the same set of people still have money. So that's fine. But notice that we have sort of run out of budget. I don't think we can fit anything else in. How much did we pay for the book? 270. So we have only 30 rupees left. And sadly, both the folder and the pen are too expensive. So we stop here because we've run out of budget. So you run out of budget, you run out of projects, you stop. Okay. So, all right. So a little bit left. That's too bad. Okay, that's what it is. Okay, so this is an example from the paper, but I'm not sure that I want to. Okay, so this is just to say it's not just fun and games. There are scenarios with more realistic projects like the ones that Pallavi already talked about, where these things are serious matters. Okay, so hopefully you're already sold on this from the previous talk, so I won't belabor the example, but I'll just go over the formal setting once again. Yeah. Yeah, so I'm going to talk about that. I was kind of fuzzy about it because I had to work through that example. I picked numbers that were easy and that I could divide. But yeah, we'll talk about the more general setting in just a bit. So yeah, let me just, yeah, so we saw one implementation of equal shares, and hopefully we have a feel for how it works, but let me just run through what the mechanism does in a more general sense. So remember that the input is more or less what we said it is, except remember I said voters express their preferences in more than one way. And in PB, normally you think about approval voting as the simpler model, but you could also do utilities, and utilities are typically additive, although you could also look at more general scenarios. So with utilities, you could say something like, as a voter, I have 10 points and I get to distribute those points across the projects that I care about in a more weighted sense, instead of just doing the swipe left, swipe right. It's a more fine-grained way of expressing your desire for your projects. Yeah, so the things you care about. But we'll mostly not be looking at this setting. I'll continue to work with approvals. So here's the mechanism again. So to begin with, the budget is divided equally among voters. And then if you find projects that voters who support the project cannot afford, so you have a project, you look at everyone who says yay, you add up all the money they have, and they don't have enough to support the project, then you get rid of the project because there's no way this is making it. Okay, so yeah, so that's the same thing, just said differently. So of course, if you run out of projects in this way, then you stop. But on the other hand, what you do now is calculate the effective vote count based on the amount of money that people have left. So this is probably part of Ashutosh's question. So I'll talk about this with an example, just so that we are clear about how the effective vote count is actually counted. Then again, we pick the winner among these freshly calculated votes, and then we split the cost of that project as equally as possible. So again, this is a little bit fuzzy because different people may have different amounts of budget remaining. So how do you split the cost equally if not everyone can afford to pay? They're divided by, how many of us supporters there are. How do you take care of that? So let's look at both of these things now with an example. So yeah, so voters, of course, who are out of money don't count. So they don't contribute to the effective vote count at all. Now, voters who have money left, but not enough money to pay for the truly equal share of the project, they will count as a fractional vote. And we'll see how those fractions come about. And in terms of the cost splitting, again, the cost is split in such a way that among the voters who approve it, the maximum payment is as small as possible is what you want to ensure. And this is easy to ensure. I think it's easier for me to show you how this is done with an example. So I'll just walk you through an example. So here, for example, let's say we have a pen that costs $60 and we have 5 people who are supporting it. Unfortunately, 2 of them are poverty stricken, have no money, but 3 of them have 30, 30, 10, and they're trying to support this cost of $60, which between them, they can. In fact, both of these guys can just cough up, but we want to distribute things equally. So what we're going to do is get this guy. So the true split cost of 60 between 3 people would be 20 each. But this guy here has showed up to dinner with a half-empty wallet, so we'll just get him to pay whatever he has. And then the remaining cost, which is $50, will be divided equally among these guys. So these two fellows here count as a full vote because they have done more than their fair share of paying up. This chap here will count as a proportion of whatever these guys paid, right? So yeah, does that make sense, sort of? Yeah, in terms. Oh, is it? So let's see. So these guys paid 25 each. Yeah. And so 10 is 0.4. Yeah, okay, sorry, that should have been, you're right, thanks. Cool. All right, so that's, yeah, there's probably more typos around, yeah.
The vote share is what you pay compared to the match that is paid, right?
Yeah, exactly, by other people. Yeah, as opposed to, I think I was probably just staring at 30/10. That's not, yeah, it's the maximum that others are paying. That's right. Yeah, thank you. All right, let's do an example from the EqualShares website. I'll just quickly walk you through this. So suppose you have a project that costs 5 units, and let's say this is the situation. You have 3 voters. So these are all the voters who support the project, but they have 10, 10, 20, and 30. Yeah. And 30 each. Okay, so that's how much money they have. And right now it only costs 5, so everyone can pay 1, everyone contributes 1 to the vote share. If it costs 10, that's still manageable. Same for 15, 20, 25, 30, 35, 40, 45, 50. So far, people can share the cost equally and we are good. What if it's 55? Well, now these folks are out of money, but they still pitch in with whatever they can. And that extra cost is divided here equally. And now notice that whatever these guys are paying, these folks have a vote that counts as a proportion of what these fellows are paying here. Does that make sense? Yeah, okay, cool. So this continues for a while. At this point, our second richest dude here is also out of funds. So this guy bears the cost, continues bearing most of the cost of the project. So this is what that split looks like. Yeah. And what happens if the project costs more than 80? Well, that means everyone who supports the project, even when they pull in, come in all guns blazing, they still can't afford the project. So at this point, I think you're just very sad. So at this point, you can't support this project anymore. And I also think that I had some additional slides. I should probably refresh this. Sorry, folks, give me a second because I think you could say that, yeah. Mm-hmm. Sorry, I just remembered I put the slide in and it wasn't there, so I had to refresh it. Okay, all right. So anyway, so when the project costs more than 80, you can't afford it anymore. So that's what's happening. All right, so okay, so this is mostly advertising picked up from the from the way it's presented, partly in the paper, partly on the website. These things about having more equal voter satisfaction and reduced bias towards popular categories of projects are mostly things that they validate empirically. They have a lot of data demonstrating that equal shares works out nicer than many of the other popular participatory budgeting systems that are in place. They're also formal fairness guarantees, and there are lots of, again, I think, as I said earlier, comparisons with other voting systems to kind of showcase the contrasts. And most of the time, equal shares turns out to be nicer on many axes. I will mostly focus on telling you a little bit about the math fairness guarantees that are promised by equal shares. And then we'll round this off by talking a little bit about EJR code and FJR in the PB setting and what we have so far in the context of those axioms. But here's like, here's a few individual properties that are probably worth talking about. So, so this is this is not a very strong property, but it's still a nice to have. So a project is guaranteed to be funded if its exclusive support is proportional to its relative cost of the whole budget. So suppose, for example, that there's a project whose cost consumes 5% of your total budget. And if at least 5% of the voters vote exclusively for this project, then that project is going to make it with equal shares. Okay, so it seems like a slightly strong assumption, but it's still a nice to have because even the greedy algorithm does not have this guarantee. Okay? So this is already a point of contrast that works in its favor. So I don't know if you want to stare at this, but this is like a simple argument. So basically, what we are saying is, now that we have so many voters voting exclusively for this project B, right? And because of the way equal shares work, these voters have B over N leverage from the beginning. That's how much each of these voters have. That's how much money each of them have to play with. And so their combined leverage is, well, these many voters, this much share, and this adds up to the cost of the project. Yeah. So because as long as you have budget, equal shares is going to continue allocating. This project will make it at the end. Yeah. Okay, that adds up. Cool. All right. I think it's important that we assume that these voters exclusively vote for the project P. When you drop this assumption, I think you can come up with examples that show that the claim doesn't quite go through as you would hope. Okay. All right. Now, what about groups that have similar votes? So this is going back to our discussions about representation. So a general hope here in lay language is that if you have a group of voters who have similar interests and who have similar inclinations, then they hope to be represented in the outcome to an extent that's proportional to their monetary leverage in the system. Okay, so if they have buying power, then they should be able to purchase the projects that they want, right? Yeah, exactly. Yeah, so we're trying to bring in an analog of JR, EJR, and so on, right? So this is the sort of thing that we want to get to, but a group of 20% of the voters is, but it's not just any 20% of the voters. These are 20% of voters who are reasonably agreeable in their opinion. So we want to talk about people who have a cohesive mindset when it comes to their preferences. Okay. All right. So in particular, let's look at an extreme example of a cohesive group. This is when we want to talk about groups who have identical votes. They think exactly the same. Okay. So this is reaching out to some sort of a mob mentality scenario, but yeah, let's talk about that as a special case. So, so say that T out of N voters submitted an identical ballot. They love the exact same set of projects. So here are 5 people who love exactly these 3 things. And suppose they can afford it collectively, right? Then it turns out that equal shares will actually select all of these projects. So that's pretty cool. So, but this is a slightly extreme. I mean, it looks like an impressive outcome, but it's based on a slightly extreme assumption, right? We're saying that here are people who like exactly. So remember that none of these folks vote for anything else other than this, and they all vote for all of these 3 things. So it's a slightly extreme assumption. The nice thing is that even a slight relaxation of the statement is true. So suppose they can't afford it, but there's a sense in which equal shares is still reasonable in its outcome. And let me try and explain what equal shares does when this group can't afford the whole set, but they still have a combined vote for this exact same. So all of these guys vote for this set of projects. They all like exactly these projects, but it's a little bit above their pay grade, so they can't afford the whole thing. So equal shares output something. The output has the following guarantee. So these are the things you're happy about. And if you try to add anything that was not picked, then it's something that you can't afford. So the purple region plus this additional project, you can pick any project you want that's here. When you add it to the purple thing, you can't afford it. So these kids can be pacified by saying that, look, we did our best, right? So because anything that we left out on top of what we already picked, that's something that really wasn't something that you could have afforded anyway. So it's kind of justified in some sense. The purple plus the red is not, yeah, exactly, for this group. And this is true for each of the red things that's out here. Yeah, exactly. Yeah. Correct. There's another sense in which we're going to talk about the up to 1 thing in a bit. So I hope that won't be confusing. But yeah, I mean, for each of the projects that were left out, it will turn out that they were not affordable anyway. So somebody implementing equal shares should be able to console people who might be unhappy about their stuff not being selected in this scenario. Are we good? Okay. All right. So, okay, it's a bit much to expect. There isn't actually, and I think equal shares fails Pareto optimality, unfortunately. So that's one of the big downers. But yeah, can't have everything. But okay, not formally, but I think. Oh yeah, sorry. For real? Okay, all right, good. So yeah, okay. So that's just what we just said, but said properly. Okay, let me move on. So mob mentality is a bit much. Expecting a lot of people to have the exact same vote is a very strong assumption. So what about people who have similar opinions? So one way to capture similarity formally is to say that, we are going to, well, all of us are going to vote for all the projects in T, but we have the freedom to also see other people. I mean, to also vote for other projects. Yeah. So yeah, so that's a slightly relaxed version of the mob mentality situation, and assume that the total cost of all of these projects is affordable by this group of people. Then what we are saying is this is the EJR style guarantee. So, well, not EJR, but yeah, okay. What we want to say here is that at least one of these voters will be sufficiently represented in the outcome. So it isn't quite as strong as saying that everyone will have representation, but at least one of these folks. Let's assume that these are all friends and they're the nice sort of friends who are happy for each other. So if at least one of them sees light of day, hopefully the whole group is okay with it. So that's the sort of thing that we want to say. So sufficiently represented, what does that mean? Well, we want to say that there's some member I for whom I can say that if they look at the projects that were selected and they look at the projects they like and they look at that intersection and they look at, well, here are all the projects that I like, how much did they cost? That's at least the cost of T, which is the common set of projects that they like. That's what we mean by adequate representation. Okay. Unfortunately, equal shares doesn't quite guarantee this. This is also kind of strong, but you can guarantee it up to the loss of one project. Okay. So this is a weak sum JR. Okay. I don't know. Yeah. All right. So this is doable. So basically, when a group of sufficiently like-minded people come together and they have enough leverage to buy out their common project, equal shares make sure that at least one of them is happy, may not be on the common set, but at least individually happy to a large extent. That's what we're saying. It's MPJ and T. Yeah, that works. Right. So that would have been a stronger thing to say, but I don't think that's guaranteed as far as I could tell.
Intersection of their
Correct. Yeah, that's right. Okay, how much time do I have? Okay, cool. All right. So so EJR in the PB setting, I think I've been skirting around it. Let me just say that, well, suppose you have a set of voters S who have leverage on T projects. And let's say that these fellows approve everything in T. So EJR would say that in the winning set, so this is basically without the minus cost of PJ. In the winning set, at least one voter has representation. So this is the notion of EJR in the PB setting. The PB setting also has a stronger notion of fairness, which is called the core, where, okay, so here we say it's basically, okay, let me just say it maybe, a set of voters blocks an outcome if there is a set of projects that's affordable for them that they prefer over what was in the outcome, okay? So what do I mean by they prefer T to W? I mean that when they look at T, they approve, each voter approves more projects in T than they do in W, okay? So I don't know if that makes sense. So each member of this set S, when they look at T and they look at W, they find T to be strictly more attractive than W. They see more projects that they like in T as opposed to W. Okay, and I keep saying like, etc., because I'm in the approval setting. All of this can be extended to utilities language. So anyway, so this is the scenario. So W is in the core if it's not blocked by anybody. That's the idea. And EJR is a special case where you have additional constraints on T. You're basically saying that T needs to be liked by everybody. That's in the intersection of everybody's approvals. You drop that assumption, you get something like the core. So core strengthens EJR as a demand, as a demand concept. And we unfortunately don't know if it exists even in the multi-winner style world. But of course, in a more general setting, if you have general additive utilities, there are examples of instances where the core is known to be empty. Okay, so this one is a big open question. So thanks for confirming that. I don't keep up with the literature so far. I know it was like resolved recently, but since you're confirming this, I will say that this is a big open question. Yes, all right, good. So yes, all right. And this is like, yeah, I mean, this is considered one of the major open problems in the area. This is true. These folks come up with an intermediate notion that they call FJR. I think it's called fully justified representation. Basically, you try to weaken the cohesiveness requirement, but not completely throw it away, which is what the core does. Okay, so essentially, okay, so maybe given that I'm running out of time, let me not subject you to all the blah, 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 but basically it's a natural intermediate notion of representation. And what we have is that equal shares fails EJR. Any efficient mechanism fails EJR, and that's kind of known. any strongly polynomial mechanism is known to fail, cannot have EJR as a property. Equal shares does satisfy EJR up to one project, and so that's the sense in which it partially satisfies EJR. Both PAB and equal shares fail the stronger notion. But the stronger notion is satisfied by a different voting rule, which is some sort of a greedy PB mechanism. However, that's not polynomial time. Okay. All right, so that's where we have. Equal shares has a bunch of other nice properties that it satisfies and things that it doesn't satisfy. And notably, it's not Pareto optimal, so that's not so nice. And let me just move on and say that I found out about equal shares from Twitter, actually, where it came up on, there's some Polish newspaper thing that Dominic tweeted about. The article is unfortunately in Polish, but it's kind of exciting that they actually implemented equal shares in a couple of towns in Poland, and it seemed to work out well. And also some place in Switzerland, which I think is nice. So I think our open problem is to see if we can do this kind of end-to-end take our algorithms, talk to the policymakers in a DESI setting. There's something that has been attempted apparently in Pune with some mixed outcomes. It'd be nice to see more people get involved in that sort of conversation. So that's, I think, the main thing that I was hoping to trigger with this by talking about this. But also, I think there are a few other things. The FJR algorithm, I'm not saying this, the authors don't like the algorithm seemingly. So in their paper, they're like, the algorithm is not terribly natural, so can we come up with something nicer? So I'm just repeating that. So Pareto optimality would be nice to have for sure. So, and some of the other stuff would also be nice to fix. So. Oh, okay, is there, okay, so you mean the EJR and PO may be non-compatible? That's possibly true. I don't know off the top of my head. Yeah, so I don't remember. Do you remember seeing anything like PO and EJR being incompatible? Correct. Right. So for the approval. Correct. Yeah, so maybe there is an incompatibility if you combine efficiency or something like this. I don't know. Yeah, because here already EJR and efficiency are at loggerheads. So yeah. All right. So yes, I don't know if the axiomatic perspective will be useful for the sorts of extensions that Pallavi was talking about, but I think it's nice to think about. In multi-winner votings, domain restrictions turn out to be extremely useful. And there are lots of nice voting rules that work well when the votes have nice additional structure. I don't know if that's been exploited fully in the PB world. And of course, the core is a big open problem for anyone who wants to take that up. All right, so I think I will stop there. Thanks so much for your attention.
When say efficient mechanism is like slides before, what does it mean? It's shown to be FPR.
So I think strongly polynomial, so did I say somewhere I said, as does any efficient mechanism. So I think there's a theorem to the effect of if a mechanism is strongly polynomial, then it cannot also be EJR, I think. I don't know if there are other qualifications to that, but I do remember the justification for equal shares not being EJR being that it's a polynomial time mechanism. So I'm taking the contrapositive and assuming that that's the kind of result they have. So let me sanity check that. Don't quote me on this, and please don't put this up on YouTube. But yeah, this is, but on the other hand, yeah, so let me double check that for you. Yeah, but. Oh, that's a great question. I haven't, in the PB setting, I think, I don't know, but work on ranking is relatively sparse in the PB world, I think. Yeah, so for some reason, yeah, I think we were also looking at it a long time ago, so maybe things have evolved, but I remember having the sense that, that's true. That can perhaps be extended to, yeah, I mean, accounting for not just, yeah, this is true. Yeah, you could do, yeah, I think you could repeat this mechanism accounting for priorities as opposed to just, yeah, thumbs up, thumbs down. This is true. I think that would be worth looking at, yeah.
The data sets are there?
Yeah, they have everything. I think their website's really well done, and yeah, correct. Actual data sets from these 3 towns. They also have a bunch of Python code that implements the mechanism, and you could try it out on other data sets, which they've also done to some extent. So there's a lot of empirical studies that they've done. Again, comparing retrospectively, I think the Paris thing that she was talking about earlier, I think they've said that, well, if you had run equal shares instead, here is how the outcomes would compare. So they have case studies of that sort as well. So it's fairly detailed, I think. Oh, I'm not doing anything, but this was more. No, this is true. I think this is my this is just my theoretical rant about, well, we should probably be doing more of this, yeah, because there seems to be evidence that it can be done. I think that's encouraging. Yes, that's true. There is a case study, and I think this sense in which perhaps also some projects and some budget allocations in Delhi at the state level were also done in a somewhat participatory fashion. But clearly not enough, yeah. Seem to be open to it, seem to be trying. Right. Well, yeah, this one is from this year, I think. Yeah, so these are all fairly relatively recent instances of the use of PB in the wild. And I see no reason for not doing more of it here. So I think that's, yeah, it would be nice. Okay, you said you had 2 questions. So did I miss another one? Mm-hmm.
For all substance.
Correct.
That has a co-NP.
It has a co-NP flavor to it. That's, yeah, off the top of my head again, I think I should know this, but yeah. I don't know if a given assignment certifying if it's EJR, at least off the top of my head, like you said, I don't see that it's easy to certify. Sorry? It's co-NP complete? Yeah, okay, there you go. Yeah. Yeah. I wasn't kidding about deferring all my questions to either Rohit or you. So anyway, all right, good. So EJR is hard to validate. So given an assignment, so Siddharth's question was, given an assignment, can you validate that it's EJR? And there's, according to sources, this is NP, co-NP complete. So yes, okay, all right, good. Okay, maybe this is a good time for tea. I don't want to get in between you and the break. Thank you so much. Cool.
Hello.
Yes.
Yeah.
Okay, so welcome you all to the last talk of the day and the second session. So Sudarshan Sham, coming from Aarhus University, Denmark, will talk about fair division under generalized assignment constraints.
Hi everyone, I'm Sudarshan, and first I'd like to thank the organizers for having this workshop and inviting me to give a talk. Am I audible now? Okay, so I'll start again. Hi. Okay. Hi again. Um, I'm Sudarshan, and first I'd like to thank the organizers for having this workshop and inviting me to give a talk here. So today I'll be talking about fair division under generalized assignment constraints. This is joint work with Siddharth Burman, Arindam Khan, and KV and Srinivas, all of whom are in the audience. So, and feel free to stop me at any point and ask questions to them. And yeah, I'm just kidding. Don't ask questions. Yeah. So, so going on to the next slide. Yeah. So here is a one-line summary of the whole talk I'll be giving. It is that strong fairness guarantees can be achieved under constraints with charity. So hopefully some of the terms in the line on display makes some sense after the talks in the morning. But okay, I'll talk about the setup now and we'll go through what each of the terms in the line mean. So the setting is as follows. We have some agents and each of them has a budget. So throughout this talk, I'll be saying budgets. I'll be using budgets in the sense it is used in the knapsack sense. So the budget is meant to limit the size of the goods allocated to some agent. So each of the agents has a budget. We have goods, and we have two types of goods. Firstly, we have indivisible goods. So these are the goods that can't be split. Some examples are cars or artifacts like paintings. And the second types of goods are divisible goods. Some examples are cake or pizza, which you can cut into arbitrarily small pieces and split among the agents. So we will deal with each of these cases separately. And lastly, to complete the problem statement, we have valuation and size functions. So a valuation function and gives us for each good how much value does it hold for each particular agent, and the size function likewise. And throughout this talk, we'll be only dealing with additive valuation and size functions. Yeah, they are considered to be homogeneous. So if a good G has value, let's say 10 for an agent, half the good will have value 5, and likewise for the size as well. Okay, so I'll risk repeating all the stuff you've seen in the morning, but I'll do it again so that it's absolutely clear and we can compare it with the new definitions we have. So first we'll discuss the fairness notions in the unconstrained setting, so which is what you have been seeing until now. So for the divisible goods case, the standard notion of fairness is envy-freeness. So by definition, an allocation is called envy-free if no agent envies any other agent. That is, every agent prefers her own bundle over any other bundle. So in this case, while it is interesting, while the definition is interesting in the cake cutting setting as we saw in the morning, in this particular setting, it is very trivial. It always exists and it's also very trivial to compute. So what can we do? We can just divide all the goods equally among all the agents. That will ensure no envy by symmetry because everyone has the exact same set. Right? In the indivisible goods case, we have, because envy-free allocations might not exist, we have the standard template example where we have just one good and two agents. So we'll have to give that good to some agent, and the other agent will end up envying the first agent. So we have to come up with relaxations to the envy fairness notion. So one of the stronger fairness criteria, which are like we come up with, is called EFX. It's envy fairness up to any good. So it essentially says that, let's consider two agents I and J. So we say EFX holds if we can remove any good from agent J, and then agent I will stop envying agent J. So that's a relaxation to envy freeness. So we're relaxing the criteria by saying we're allowed to remove any good from agent J's bundle. Okay. So now the overarching question we will address in this talk is, what about the constraint setting? So what happens if not every partition is feasible? What happens if only some, or we can only assign some goods to some agents or something of that sort? So now we talk about a new, not a new, but a different, slightly adapted fairness notion called feasible envy freeness. The first thing to observe is that envy freeness cannot be guaranteed in the constraint setting and is in fact unreasonable. So why is that? Let's take a very simple example. Let's take two agents and identical valuation and size functions for all the goods. Let's say the first agent has a budget of 1 and the second agent has a budget of 100. So it's reasonable to expect that the second agent will have more value, right? So as a concept, envy freeness does not make much sense over here, because agent 2 will obviously have more value because he has a higher budget. Yeah, so this is the reason because of which envy freeness is unreasonable. Agents have different budgets. So the way to get around this is to change the notion of fairness slightly. It is that we say we only compare feasible subsets of goods while checking for envy. So let's take this example. There are two agents, the green agent and the red agent. So they are already allocated some goods. So let's say we want to check if the green agent envies the red agent or not. So what we'll do is we'll look at every feasible subset in the red agent's bundle. So every subset of goods that fit in green agent's bundle. So one example is the yellow circle in the figure. So and then the green agent will compare the value, her current value, with the value of that particular subset. No, it's by budget. So a budget, yeah. So, a size, yeah. Yeah, but also note that it's so we'll deal with a very general setting. So the size can be different for different agents. Yeah. 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 Yeah, that's right. Yeah. Right. Yes. So there's one more thing I'll add to the setting. So we saw the construct of charity in the morning, but there it was meant as a way to get rid of some goods. But here we kind of cannot get away without the concept of charity, because we have some constraints. So we are bound because we have constraints, we have budget constraints. There might be many items, so it might not be feasible to allocate all the items to the agents. So let's say every agent has a finite budget, right? So let's say the sizes of the items are much larger than the budgets of the agents. So we'll have to assign those items to the charity. So we'll have to discard them. There's no way to give them to the agents. So we'll have to define the construct of charity in this setting. Okay. So here are the main results of the talk. So these are the two main results. The first result concerns divisible goods. We show that under the definition we just saw, there always exists a feasibly envy-free division, or FEF division. And moreover, surprisingly, we can find such a division efficiently. So there's a polynomial time algorithm to find such a division. And the second main result is in the indivisible goods case. We'll deal with these two cases separately. So we come up with a slightly relaxed notion called FEFX. It's very similar to the way we got EFX as a relaxed criteria. So then we show that there always exists a feasibly envy-free up to any good allocation, or an FEFX allocation. And we also see that it's hard to compute. So we'll have to get by with something slightly more relaxed. Okay, so now I'll start with the technical content of the talk. So I'll first talk about the divisible goods case. So let's just go over the setup really quickly again. I'll just repeat what I just said earlier. So we have agent-specific value and size functions, vi of g and si of g. So they tell us the value and size for good g. And as mentioned earlier, the goods are homogeneous. So half the good will have half the value and half the size. The valuation and size functions are additive in nature. And each of them has an individual budget constraint. So here we see, okay, so this is just a repetition of what I said earlier, but it's really important because we cannot get by in this setting without charity. So charity will get some charity. So we'll have to use the concept of charity to discard some of the items we cannot assign to the agents. Yeah.
More general than the regular integrate rate if I just throw off the size. So how is EFX exist?
So that's a good question. It exists because we have charity. So we are allowed to assign some goods to charity. So yeah.
So that's the price
Yeah. That's true. Yeah. Yes. Yeah. 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 So here's one key simplifying assumption I'll make. I'll just assume that the total sizes of the goods is much greater than the budgets of the agents. So this is a technical assumption. So if you don't like it, you're welcome to ignore it. But the reason is, and you can easily change any fair division instance into this instance by adding a dummy good with 0 value and very large size. So, but feel free to ignore this point if it does not fit. Combined budget, let's say. It's a very huge good with 0 value. So now let's just look at the fairness criteria once more. So the formal definition of feasible envy freeness is as follows. We say agent 1 does not envy agent 2 if she does not envy any feasible subset of agent 2's, the feasible subset of agent 2's bundle. So in particular, I'll mention here that it's trivial, but I'll still mention it, that it suffices to find S, which is the maximum valued feasible subset of agent 2's bundle and compare with it. So is that clear? So all I'm saying is, I want to ensure that agent 1 does not envy any feasible subset of agent 2's bundle. So all I'm saying is, instead of looking at every subset, we look at the maximum valued subset of maximum valued feasible subset of agent 2's bundle and check with it. Okay. From one's perspective, yeah. Yeah. So now, when do we call an allocation feasibly envy-free? So we call an allocation feasibly envy-free if first is, as we have been seeing all along, no agent envies any other agent. The second, a very important condition is that no agent envies the charity. So let's take a moment to consider why this is very important. This is very important because otherwise we can just have the trivial solution of giving all the goods to the charity. So every agent will get a null set, no one will envy anyone, but that's obviously not a desirable scenario. Yeah. So each agent has a budget, and each good has a size according to each agent. So a subset of goods is feasible for an agent if the total sum of the sizes of the goods is less than the budget. No, it's agent specific. Agent specific. So it can be different for different agents. So the motivation comes from many different areas. So I can't pinpoint one, but AdWords is one possible. So this is inspired from the generalized assignment problem already studied, where the size, like the constraints are dependent on the agents. Like the sizes are dependent on the agents. Yeah. So it's inspired from the generalized assignment problem already studied. Okay.
Just with check whether there is NV or not, you have to solve a small knapsack problem.
So right now we're in the divisible goods case, so you don't have to. So you can just take the, so it's not even an LP actually, like you don't even require the full power of linear programming. Densest goods, yeah. Yeah, the densest goods, that's the key point here. So now let's look at a very simple case and motivate the tougher algorithm, like the algorithm for the general case with this. So let's take the case where the value functions and the size functions are identical. So V of G and S of G denote the size of the good G for every agent. So they are identical. So this is a much restricted case than the much general problem, but it will give us many insights into what the solution for the general case looks like. So the only thing that's non-trivial here is that the budget constraints are individual. So different agents can have different budgets. So let's look at how we do that. So now let me define this quantity called density of G. It's the name is self-explanatory, and we say density, we define a density of a good G to be the value of the good G over size of the good G. In this case, it's identical, so it's not agent specific anymore. We just define density of G as follows, and it will play a crucial role in the first part of the talk. So now the algorithm looks like this. It's some kind of water filling algorithm, and so let's go into the algorithm and see what it does. First, we order the goods in decreasing order of density. So in some sense, we want to prefer the goods which are highly dense. So we'll order the goods in decreasing order of density. Then we order the agents in increasing order of budgets. And let's look at a toy example here. So we have 3 agents and 3 goods. So agent 1 has the least budget, agent 3 has the highest budget. Goods, there are 3 goods. G1 has the most density and G3 has the least density. So this is the toy example. So let's look at how we can compute a feasibly NV-free division. We can do that as follows. We can take the first good and divide it equally among all the agents. That's pretty natural, right? That's what we want to do. We want to divide everything equally. But now let's take the second good G2 and try to divide it equally among all the agents. But it turns out that we cannot do it because it will exceed the budget of agent 1, right? So what do? We just give it enough to fill the budget, right? And then with the leftover G2, we divide it equally among agents 2 and 3. Yeah, so I hope this kind of makes sense, like why I said it's a water filling algorithm. So you took G2 and you just gave agent 1 enough to fill her budget, and then divide the rest equally among 2 and 3. And thankfully, we can take the good G3 and fill up all the agents. So, but it is relevant to note that, as mentioned earlier, there is some G3 still remaining. So what do? That we give it away to charity. So the final allocation looks like this. Yeah. No, least. Yeah. Yeah, the colors are not as different as I imagined. The middle one is orange. Yeah. Yeah. So now let's look at a few observations in why this is feasibly NV-free. So the first observation is that all agents are full in the final allocation. So if this is kind of the reason why I made the technical statement earlier that the sizes of all the goods is greater than on the total budget. So now in the previous slide, we see that all the agents are filled up to the brim, right? The second more believable fact is that no agent envies the charity. So why is that the case? So I hope it's kind of clear. It's because of the way the algorithm works. We took the most dense good, we divided equally. We took the next densest good, divided equally. And something goes to the charity if and only if no other agent wants it. So no agent envies the charity by definition. So now let's look at why there's no feasible NV-free, like why there's no NV between the agents. So let's look at the simplest case first. Let's take 2 agents, I and J. So first, let's say agent I has a higher budget than agent J. So let's say, so for example, in this case, let's take the case of 1 and 3. So agent I is 3 and J is 1. So now, as it is very visibly clear, 3 will not envy 1 because 3 got more stuff. So which means agent with a higher budget will get more value. So they'll definitely not envy the agent with a smaller budget. But now comes a slightly tricky case, which is what happens when agent I has a smaller budget. So again, let's go back to the figure. So let's take agent 1 and 3. So we want to check if agent 1 envies 3 or not, right? So we use the observation made earlier that we only need to check with the highest valued subset from agent 3's bundle. And what is the highest valued feasible subset from agent 3's bundle? It is okay. Okay, never mind. So I have a line there which is on top of the one's budget, which denotes one's budget. So the part of 3's bundle below that is the maximum valued feasible subset according to 1, right? And as we can see, they are identical. So there's no way agent 1 will envy agent 3. So is that example clear? Okay, so now if we put all these observations together, we know that it's a feasibly envy-free division. So now the thing I'll do is I'll abstract out a few key properties from the algorithm and use it to derive a much more general condition. So the first observation is that all agents are full in the final allocation. The second observation is that all agents are allocated only top tau I densest goods, where tau is some vector. So in this case, so what I mean is, in this case, tau 1 is equal to 2 because agent 1 was allocated only two of her most densest goods, and tau 3 is 3 because agent 3 was allocated top 3 of her most densest goods. Okay. And now comes the slightly technical statement. It says that agent I contains the maximum fraction of its top tau I minus 1 densest goods. So I'll again go back to the figure. So if you look at the first agent and good G1, the most densest good, we see that it's equally split. So it contains the maximum fraction. It contains the fraction of that good as much as any other agent. Now let's look at agent 2 and good. Let's look at agent 2 and good 2. So the second most densest good, the orange part where the pointer is there. So now we see that good has been allocated. Agent 2 contains the maximum fraction of that good among all the agents. And so that's what I mean when I say agent I contains the maximum fraction of its top tau I minus densest goods among all the agents. So is that statement clear? Yeah. So now let's get to the general case. The algorithm follows very naturally. We define density of a good G to be Vi of G over Si of G. It's an agent-specific function now because we are talking about the general case. I'll just use one more notation, which I'll denote by Xig. Xig is the fraction of good G allocated to agent I. That's the only notation I'll use. And now I'll describe the key concept of density domination. Yeah. No, there are other ways, but it's an algorithm which does that. Yeah. So we're just inspired by that algorithm to come up with the algorithm for the. Yeah. Yeah, there are. Yeah. Sorry. So in the previous case, it's identical valuation, so it's every allocation is Pareto optimal, and yeah. So, but in the general case, we do not have Pareto optimality because we are kind of dividing goods equally. So you can never have Pareto efficiency if you kind of divide things equally without taking into account the values. But yeah, that's an open problem as well. So we can talk about it at the end. So the key concept of density domination is as follows. For some tau vector, some threshold vector tau, we say that we ensure that agent I is allocated only top tau I densest goods. So if a good G is not in top tau I densest goods of I, then its value is 0. Then fraction allocated of good G to agent I is 0. Okay. Now there is a domination condition where we say if G is among the top tau I minus 1 densest goods, then the fraction allocated to agent I is at least as much as any other agent. So the fraction of xig is greater than xjg for any other agent j. So G is the fraction of G allocated to agent I is at least as much as the fraction of good G allocated to any other agent. So that's the domination condition we have. And the last condition is very simple. It's again that all agents are all full at the end. So if these three conditions are satisfied, we say that density domination condition is satisfied. Okay. Now, why is this important? Firstly, it's that the condition density domination implies feasible NV freeness, and the proof looks very similar to the identical goods case. And I'll skip it. Like it's exactly the same. It's almost exactly the same. Secondly, it's also interesting because given a vector tau, density domination can be written as linear constraint. So it allows us to model this problem as a linear program. But the problem is we don't have a tau yet. We don't have the threshold vector yet. So the non-trivial task is to find such a threshold vector tau such that the linear program is satisfied. If we do that, then we can use the linear program to find the actual allocation. So the algorithm looks as follows. We initialize all the taus to 1, so which is very natural because to each agent we want to give the most densest good according to them. So we say, yeah, we initialize all taus to 1. So now we check for density domination. We do that by using the linear program we had. If it is feasible, then we are done. We can just return the allocation, the linear program outputs. But if not, what do we do? So very intuitively, the reason the linear program might be infeasible is that at least one agent is not full. So at least for one agent, there is still space to allocate more items. So what do? We try to allocate more items to that agent. So basically, we choose that agent and increment the tau for that particular agent by 1. So we increase the goods allocated to that agent. And we keep doing this. So the thing that it always terminates with a tau that satisfies the linear program requires a proof, but I'll not get into it. But it's very intuitive that intuitively what happens is we are starting with all taus to be 1, so all agents are not full. Then we keep increasing taus until all agents become full. Anyone, yeah. No, just one, yeah. No, then it might be infeasible, right? So you're basically dividing every good equally. Then some budget constraint for some agent might be. Yeah. So firstly, if you believe me on the previous slide, we have a polynomial time algorithm because we have a n-dimensional vector, and we are increasing at every step. We are increasing at least exactly one value by 1, and so that whole process can take at most mn time. And at each step, we are running a linear program. So overall, it's a polynomial time algorithm. Okay, so we use linear programs for density domination, like to check density domination. And another key technical point is that this algorithm does not use fixed point arguments to prove the existence. So we in fact prove the existence of such a fair allocation using a constructive algorithm, which is very efficient. So that's a So water filling only works if in the case of identical valuation and identical sizes. So if they're different, then it's not. So then it's no concept of densest good because the densest good differs from between agents, right? So that is what we are doing, but it requires so then we divide equally, right? But then some will get very much in the first round. So yeah, the constant rate does not work because the budgets are different, and the constant rate does not work because yeah. 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 So this is the main result for the divisible goods case. So we prove that there always exists feasibly envy-free division, and we can find such a division efficiently. So, yeah, I'll move on to the indivisible goods case in a moment. So we have indivisible goods in the indivisible goods case, obviously. We have, again, using the standard template argument, one good, two agents, feasibly envy-free allocations do not always exist. So now we define a relaxation very similar to the EFX notion defined in the unconstrained setting. We call it feasibly envy-free up to any good. So it's called FEFX. And yeah, so now the formal definition of FEFX is as follows. We say agent 1 does not envy agent 2 if for every strict feasible subset S of agent 2's bundle, agent 1 prefers her own. So the keyword is here again is strict. So basically it's the feasible envy-freeness definition, but only that the subsets are required to be strict. That's the only relaxation we are making. And it's the exact same as in the unconstrained setting. So yeah. And so a way to look at the FEFX definition is as follows. Let's say we want to check if the green agent envies the red agent according to the FEFX definition or not. So what do? We remove any good from agent 2's bundle. So let's choose any good. Let's take the red good, remove it from agent 2's bundle, and check for envy-freeness, check for feasible envy-freeness. So that's a natural way to look at FEFX. Yeah. Sorry. So this one is much stronger, stricter, because essentially you can always remove one more, right? So we already removed this, so you can always remove one more, and so this is a stronger definition of FEFX then. Yeah, I'll skip this slide for now. So before coming to the algorithm, so we have a constructive proof that an FEFX allocation always exists. But before coming to the algorithm, I'll first note a few things about the problem. We first show that computing an FEFX allocation is NP hard. Yeah. Yeah. So yeah, existence is always there. So yes. Yeah. Yeah, that's yes. Yeah. So that's part of the definition of feasible. So always everything feasible is, whenever we say feasible envy-freeness, we have to define charity. So
this may not always
fine. Yeah. Knapsack. No, not I think it's no, we use standard knapsack. We don't use unbounded knapsack. No, I think for this one we don't. Okay, yeah, we can. Yeah, we do the binary search on the value. So yeah. Okay. Okay. Yeah. Yeah, but it's NP hard, so that's for sure. Yeah. So we do the next best things possible, which we say that we give a pseudo polynomial time algorithm and FP test for the problem. So given that it's NP hard, that's all you can do. So and the idea of the algorithm is very simple. It is that we swap minimally NV sets, and it is inspired by previous work by Chaudhary and others, who did this kind of the same thing, but in the unconstrained setting. So I'll get to the algorithm. It is very simple. It is very simple and elegant, but the problem was hard to figure. So first I'll define the concept of minimally NV'd subset. So the definition is as follows. We call a subset of goods minimally NV'd if it is NV'd by someone and no agent envies any strict subset of the goods. So in some sense, you can visualize it as the smallest set of goods that some agent envies. So that's a good way to visualize the concept of minimally NV'd sets. Yeah. So whenever we check for NV, it's feasible NV freeness. So basically minimally NV'd subsets basically means we look at the smallest set of goods someone envies. So now the algorithm is as follows. We start with all the goods assigned to charity. So initially all the goods are assigned to charity. So all the agents have empty bundles. So in each step, we choose a minimally NV'd subset and swap the goods of the agent who envies it. So I'll use a figure to denote it. So let's say, let's have this toy example. This is an intermediate step in the algorithm. So each of the agents have some bundle and the charity has some goods. So let's say this is the minimally NV'd subset, the circle and the gray shaded portion. And let's say the red agent is the one who envies that agent. So all we do is we swap those two bundles. So we do this. And we keep doing this again and again. We keep doing this until no agent envies the charity. So until we cannot, we keep doing this again and again. So, and that's just the algorithm. So it's just that simple. Yeah.
Nothing to the
Yeah.
So everyone minimally
One. So the first minimally NV'd subset will be one good. So so you can pick an arbitrary agent and swap. So you can give that good for a while until all the other agents get one good. Yeah. 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 Sorry. Yeah. No, not with agents, with charity, just with charity. So it's more clear when I go to the next slide. It's first that swapping minimally NV'd subsets always ensures that FEFX is maintained among the agents. So they can't swap between the agents. So we maintain FEFX and we swap only with the charity. And further, stopping condition ensures that no agent envies the charity because that's when we stop. And the last point is that this algorithm will terminate because in every step of the algorithm, exactly one agent strictly increases their value. So we are heading towards, we are giving more value to the agents in every step. So yeah. And yeah, so that leads us to the main result, which for the indivisible goods case, which is that there always exists a feasibly NV free up to any good allocation. So I'll go to the summary and then have some open problems at the end. So the summary of the talk is as follows. We saw two cases, one with the divisible goods case, and in the divisible goods case, we defined the concept of feasible NV freeness, and we showed that a feasibly NV free division is guaranteed to exist. Further, we gave a polynomial time algorithm to find such an allocation. In the indivisible goods case, we came up with a relaxation of feasibly NV freeness called FEFX. We showed that always exists, and unfortunately, finding an FEFX allocation is an NP hard problem. So we do the next best things possible. We give a pseudo polynomial time algorithm and an FP test algorithm. So going to the last slide. So here are some open problems. In the divisible goods case, the problem is to compute a Pareto optimal feasibly NV-free division efficiently. So so we have fixed point theorem proof of the existence of such a division, but it's not known whether we can compute it efficiently. There is a trivial exponential time algorithm which involves enumerating all the polyhedra and looking at all the vertices, but the question is, can we do it efficiently? In the indivisible goods case, we can potentially consider other types of constraints, most importantly, Metroid constraints. So an interesting thing I'll mention here is that the FEFX algorithm we saw, the swapping with the charity, swapping minimally and we subsets with the charity, it gives us FEFX in a very different, very general cases of constraints. So Metroid is one of them. But the complexity of computation of FEFX allocation in the Metroid setting is not known to be NP-hard. And it is possible that there exists an efficient allocation to compute it. And the very last question is, are FEFX and Pareto optimality compatible? So the smiley face is at the end is because it kind of asks the EFX question inside it. So if the answer is you can always do it, then you say that EFX exists. But on a more serious note, you can consider approximations to Pareto optimality. So the current algorithm does very badly on Pareto optimal front. So the open problems are, can you do better? Can you find a constant approximation to the Pareto optimality? With respect, all the feasible allocations.
Well, then, I mean, without constraints, we know that it's allow zero values in EFX and Pareto optimality are incompatible.
Yeah, with zero value, without zero values, I guess. Yeah, that's the question.
So then it's only with respect to the compatibility of all.
Yeah.
Let's say that there is a problem. That's why it is fine. You're forced to have everything. The Pareto optimality is with respect to all allocations that are. But this doesn't decide the answer. It does not force you to have everything.
Yeah. Yeah, that's the. Yeah. Yeah. Not sure. So
we do know that half intercepted doesn't. Does it give something to half?
no. So in the whole work we only considered absolute, not like exactly FEFX allocation. So we didn't consider any approximation to the feasible NV-freeness. Yeah.
How does this compare to Saudi or charity? Meaning, if I just don't care about the budget and everything, if I run the same swapping algorithm,
yeah,
will I end up with the same allocation with n-1 charity?
So they do something more to minimize the number of goods, which we do not do. So the only condition is no agent will envy the charity. That's the only condition we ensure. Yeah, that's true. Yeah, and so yeah. Additive. Yeah. And each of the goods have positive value, let's say. Sorry?
In the divisible setting, identical values for
yeah.
But we have a charity as well.
Yeah. So in the identical setting, the algorithm we described is Pareto optimal because we are giving to charity only when no agent, least density goods. So
there could be on Pareto optimal.
Yeah. Yes. Yeah. I mean, so that's so we can construct a trivial example where there's one good and we divide it equally among the agents, but we also give some to the charity. So we divide it equally among all the n+1 agents, where the n+1th agent is the charity. So we can always waste stuff if we want to. Yeah. Yeah. Okay, so that's the end of the talk. Yeah, thanks.
Added a large code.
Yeah, it's binary search. Yeah.
Okay. So it's supposed to be an open session now, which means I don't know what's happening now. But there is an open problem session also tomorrow. So, if you have open questions which have not come up during the talks, if there's some other kind of related topic you wanted to introduce briefly, um, you know, we can do that tomorrow. Or if anybody has a brief open question they want to talk about today, that's fine. The other thing I wanted to say is that, like I said, so we've been trying to do this some game theory related conference reasonably frequently. If you have suggestions, if you want to organize something, if you want to advertise something related that you're organizing or plan to organize or would like to organize or would like us to stop organizing, that's fine. You can tell us. That's yeah. I mean, basically all I'm saying is somebody else wants to grab the mic from me, do it now. Ganesh is Ganesh here? No, sorry, not Ganesh. Girish. Girish had some announcement regarding the mentorship session during FST, but he's run off, so that's not happening. Yes, the PhD clinics. He wanted to say that some PhD clinics are today, but he's run off, so I don't know. Yeah, so I'm going to put the mic here. If anybody wants to grab it, sure. Otherwise, feel free to break out and, just come back tomorrow or whatever.
Pass on suggestions.
I would also like to thank both the organizers.
Right.